كذبا. also. बहुत हाई लेवल चीजें ही हैं। एसिंग रस्ट है।
All right, let's understand a few extra concepts. Map, filter, and arrow functions. Map and filter.
Rest of the text. Now, on the other hand, for example, this H2 element here is a so-called block element, because as we see here,
filter and arrow functions. Map and filter.
Filter is written in array map. Let's 2, 3, 4, 5.
Map and filter are sort of helper functions when it comes to arrays, and arrow functions are just another way to write functions like this. Maybe let's start with the easy one, which is arrow functions. Until now we have written functions like this: function ab return a plus b, and then I can call const answer equal to sum of 1 to console.answer. This works. This is totally fine. You can always write functions like this, but a lot of times functions are written like this. Now look at the syntax and how it changed from this to this: const sum equal to a function with these arguments, arrow, and then curly braces. Both are almost exactly the same. They are not exactly the same. They're the same in this context, but eventually when you will write structurally, cool. That's one. Map and filter. Let's structurally, cool. That's one. Map and filter. Let's get to the difficult ones now. Okay. Now, let's say I give you a problem statement. Always good to learn things by problem statement. The problem statement is given an array, give me back a new array in which every value is multiplied by 2. Cool. Which means if the input is 6, not 2, and then this is okay. The input is 1, 2, 9 to this output array. Multiply every value by 2. Cool. If I change the problem statement, can you multiply every value by 3? Hopefully that's straightforward as well. 3, 6, 9, 12, 15. So this is one way of solving this problem. But the JavaScript head thought, this is very early. So let's make it slightly cleaner too. We know one thing about JavaScript. Okay, bhaiya, in JavaScript, a function can actually take another function as input, right? And then you can actually call this function. This was A. I can actually call A here. So a function can take another function as input in JavaScript. What if this transformation that we want, I define in a function. I say, okay, bhaiya, function, give me an input I, which is a number, and I return back to you I into 2. The transformation that we need to do, I wrote inside a function. Let me call this function f, or whatever. You can call this function whatever you want. I'm calling it f. I defined a function. I said I take an input number and I return that number into 2. Now that I have this, wouldn't it be nice if there was a function called map? Let's say there was a global function which took number 1, this array as an input, number 2, this function as an input, f, and the output that it gave me was this array right here. Wouldn't that be nice? Okay, I can create an output array with the initial input and a transformation function, and then some other function, some global function called map will worry about how do I take each one of these values, how do I put them in the transformation function, and how do I create a new array from it. That is what the map function lets you do. The syntax you will see very soon, but what is the goal? The goal is that given an initial array input 1 2 3 4 5, given a transformation function f, which in our case is function take a value as input, return input. Given these two things, r comma f, can we create this third function, which is just f passed into a global function. We don't have to create this. This is provided to us. We just have to give it two inputs, the array and the transformation function, and it gives us the final output, which is 2 4 6 8 10. That is what map lets you. Rather than doing all these things that we have done here, I can simply be like, const, let's just say other solution. Let me just comment this whole solution out. Other solution is function transform I return I into 2. Just define a function. I can call this function normally. Transform to const answer equal to this. If I log answer, what will I see? I will see 4 on the screen. So this is just a normal function. Thankfully, JavaScript said, if you have a transformation function and you have an initial input, give me both of them. I will transform each one of these values and give you the new output. So now if I call map with arr comma transform, would be nice if this gave me the output of 2 4 6 8 10. This is not the right syntax. Would be nice if this was the function, but the function looks slightly different. Map exists as a function on the array class, so I can actually do something like this. By the way, this should have been input, but you get the idea. I can do something like this: input dot map transformation function, and that's all. Const answer equal to this, console.log answer. And now if you look at the output, it says 2 4 6 8 10, which means in just one line of code, effectively 4 lines of code, but assuming transform is a sandbox, which you cannot know well. Okay, 4 lines of code in 1 2 3 4 lines of code. I was able to do the same thing that here took me 4 lines of code, but hopefully you get so this is slightly cleaner. Now it's debatable what is more cleaner, what is not, but this is used whenever you're being told to transform arrays. You use map. And if you look at the syntax, what does it do? Feel free to ignore this. Feel free to ignore this. Let's look at just this much. It says input array is this. Input array dot map convert every value, transform every value through this transformation function and give me the output. So 1 will go through this transformation function and be put as the first element here. Then 2 will go through this transformation function and be put as the second value here. So on and so forth, one by one, all of these values will get transformed, and by the end of it, you have the answer array that looks like this. That is one. The other clear syntax to usually write this is you actually don't define your function separately. You just put it here. Okay, const answer equal to input.map, and then you just give the function here. Okay, this is my transformation function. Please transform every value by passing it through this transformation function. Every value individually goes into this. How it happens is the implementation of map function. You can actually write this yourself. Take this as an assignment. Create a map function that takes 2 inputs, an array, and a transformation callback or call it function, and transforms the array into a new one using the transformation function. Cool. Feel free to take this as an assignment to do it yourself, but you don't have to. Thankfully, JavaScript just gives it to us. We use it as a black box. Yeah. Input.map transformation function gives me a transformed array output. Cool. That is one. What is the second thing we need to discuss? The second thing we need to discuss is filtering. Let's again start with the problem. What if I tell you, given an input array, give me back all the even values from it. So if the input is 1 2 3 4 5, the output should be 2 and 4. Cool. What's the early way of doing it? Akira, the early way is const new array equal to empty array, and then I just iterate over the array at dot length I plus plus, and then I'll be like, if array of I mod 2 equal to 0, return new array dot push array of I, and if I now log new array, I'll do this yourself. I see 2 and 4. Again, forget this. Try to code it yourself. Given this function, you don't have to worry about filter and what it is. Given this function, how would you solve it? Given this problem statement, how would you, given an I, create a new I that only has even values from this? This is not going to be it. But what we are learning? We are learning the filter function that JavaScript writes. Let's see how it works. What is the input? 1 2 3 4 5. What is the question? Question is, only even values should stay. Can I say, I'm going to create a function, call it filtering logic, which will take all of these as input one by one, and it will return either true or false based on what the input is. So if your filtering logic wants to include something in the final array, if n modulo 2 equal to 0, what does this mean? If this is an even number, then return true, else return false. Wouldn't this be nice? If I could create a filtering logic function that takes n as input and returns true or false based on whether n is even. I have created this function. I have the input I. Wouldn't it be nice if I can simply call a function, this is the input I, this is the filtering function, please give me the final output which has the filtered values. So the input is 1, 2, 3, 4, 5. The output would be 2 and 4 because this filtering logic would tell कि हाँ भाई return true if it is an even value, return false if it is odd value. Might feel counterintuitive. Why are we doing this? Doesn't sound like this looks so much simpler to understand. I agree, but especially in React, filter is simple. Map is very important. You need map in 100 different places. You'll always get by without it, but this makes the syntax slightly cleaner. So would urge you to get comfortable with the syntax. And let's do that for filtering now. So first let's write a filtering logic function or filtering logic. You can call it whatever you want. Let me call it filtering logic. What will it do? If n mod 2 equal to 0, return true, else return false. And then finally, const answer equal to filter logic input array. No, sorry, that's not right. Const answer equal to add dot filter filtering logic. Again, there is no global filter function that possesses. I think I was showing you it wouldn't be nice if there is a global filter function, but global filter function or add dot filter doesn't matter either way. There is a function that exists that given an input array and given some logic to filter out values, true or false, gives you the final filter array. If I now log answer here and if I run this, you will see the string size 2, 4. So just these, not 2 lines of code, of course, it's more lines of code here, but this is conventionally considered the more clean syntax to do this versus creating a new array like we did before. And as I said, most of the times you will not be writing this outside. You will pass the callback in like this and make it an anonymous function. This is actually the right way to do filtering. But again, the problem statement is print all the even values, then you print it like this. If the problem statement was something else, okay, given the input is a lot of users, or a lot of genders, we're going to a lot of users. So Hakirat, Prash. Return me all the users whose name starts with H. Then your filtering logic would be like, if n dot starts with H, then return true, else return false. Now look at the output, it gives me back Hakirat, given this input. Hakirat, what it starts with, any string if you have. So Hakirat dot starts with H returns true. Now I have logged it. If I log it, it will return me true. So it's just another helper function that is present on the string class dot starts with. And if I look at the logic, basically the thing to know here is the input n could be anything. It's what the individual values of the IR. If the individual values of the IR are strings, then whenever this function is called to check should this be filtered, should this be filtered, should this be filtered, the input n will be a string. And if the input array had numbers, then of course the filtering logic would check whether or not these are numbers. Cool. And then you can do like number logic in that. Right? Cool. So what do we learn? We learn two things: filter, map, and arrow functions. And maybe another thing if you want to merge them all together is something like this. You can actually, rather than writing function here, create an arrow function. Again, just syntactical difference for now, no other difference at least until this point. Either writing like this or writing like this. Cool. Filter you understand, map you understand, and arrow functions you understand. Great starting point. There are more such functions. These are the important ones. There's one quite as so many shows. Reduce, for each, spread, no, not needed if for the understanding of it all. Map is very necessary. Filter also you can know, but map make sure you're comfortable with the syntax of map, understand how it works. If you want to do the assignment was create a map function that takes an array and filtering and a transform function as input and returns the transformed array as output. If you want to take this as an assignment, feel free to. With that, I think we're done for today. And also AI gave me the answer. So yes, this looks like better to code it. I'm not using AI. Let's end it. I'll see you guys soon. Mic testing. Hello, hello.
Let's see. All right. Hello. How's everyone doing? Sorry for the delay. Hopefully you guys are having a fun Friday evening, night. It's 8:30 already. I need to do an internet check. I'm not at the best Wi-Fi right now. So let's do, 2 minutes of an internet check. If it's bad, I'll answer a few questions for the next half an hour, and then in the next 1.5 hours, I'll record the video offline. If the internet is good, then we will continue with the live video. These are the slides, same slides from last week. We did a poll. The poll said we need a live video for this, and hence we're covering this live. Ideally, we have 2-3 variations of these slides covered once in the school, once in cohort 2, once in cohort 3. So there are a few videos that sort of cover this. I'm happy to post those as well. But you guys want it live, so we'll try to do it live. I just want to do an internet check, so I'll just share my screen and check if you guys can see it. Mikey, if things go bad, let me know. But I think everything looks fine for now. Are we good to go? Can you guys hear me and can you see the slides? Can you guys hear me? Can you see the slides? Mic testing 1, 2, 3. Yes, slightly laggy, some lag. I should record this locally in that case, if there is some lag, so that you guys have a HD video ready at the end. For that, I will need to clean my machine up a bit. I have too many things here. While I do that, let me talk through my day. I had an interesting day, early flight this morning. I had to come to Kerala. I don't know how many of you guys are from South, but there's this college in Kerala that's incredibly supportive around, upskilling their kids. So next year at the 100x school, we're sort of, basically, I won't call it two separate, branches. It's not like we're opening a branch here, but we're doing some sort of a collaboration with them, for which I had to sign an MOU. You will probably see it soon enough somewhere on LinkedIn or something. That's why I'm here. I had a red-eye flight. I haven't slept much. Had to record a few videos with the folks here. And then another podcast tomorrow, and then I go back to Delhi, and then I have my birthday on the 1st. So tomorrow's going to be, probably going to spend my birthday in the flight. But it's like, I'm very old, so it doesn't really matter. We kick things off. I think I have enough space on my machine. Let me start OBS. Hello. Hello. All right, that looks good. We kick things off. We should stop the reactions somehow. Mikey G. I don't know how to stop the reactions, but I would urge you to do that. While you figure that out, I'm going to kick things off with a slightly more complex part of JavaScript, but a very language independent concept. Very nice first difficult thing to learn. I think the very first big difficult thing to learn for beginners is syntax. HTML CSS almost everyone understands like this. JavaScript syntax gets a little tricky. We did that in the last class. In this class, we're doing some things जो कई बार बहुत बाद में समझ आती हैं. You learn these things much later in life sometimes. For example, I didn't immediately for the first probably 1.5 years of my coding journey know what are single-threaded languages and what is synchronous code and what is asynchronous code. This difference between synchronous and asynchronous for me came much later in my journey. For you guys, we're trying to make sure that you know the difference earlier. It is an important difference. Eventually, we're going to learn how asynchronous is different from concurrent. But right now, JavaScript doesn't really have the concept of, asynchronous, concurrent, and parallelism. What is the difference between the three? JavaScript specifically, when you're learning, you probably need to understand what is concurrency and what is asynchronous versus synchronous. You don't need to understand parallelism because unfortunately JavaScript does not support parallelism. That is something we will cover in the Rust videos in the Web3 cohort when we reach, the syntax of Rust eventually multi-threading. With that, this is what we did until the last class. Hopefully you guys understand what are functions. Here is a very nice simple example of what functions are. And hopefully this is very simple to understand because you're going to see these from function body. You return something from the function. Whatever is returned from here, just code locally. The simplest way to post for the people who've done math, you know that the sum from 1 to n is nothing. You iterate first, what seconds in a full stack application. You do touch asynchronous. Many questions you're using what is a function, you can center. You never understand the concept of asynchronous codes because you synchronous code. Generally, when you're in college, you don't deal with these concepts. You start to solve lead code questions. You're using functions left, right, and center. You never understand the concept of asynchronous codes because you never deal with asynchronous. Code bases in DSA. When you're doing DSA, you don't ever touch asynchronous code. But when you're writing backends in a full stack application, you do touch asynchronous code, which is why we need to understand the difference between synchronous and asynchronous code. Let's start off with synchronous code. Any code that we have seen until now, any DSA problem that you might have solved, the code that you're writing is synchronous. That is a very bad definition that I'm giving, so I'll take you through a few examples. But what is synchronous code? Synchronous code is executed line by line in the order it is written in. Each operation waits for the previous one to complete before moving to the next one. This might feel like a slightly incorrect statement because what does it say? Synchronous code is executed line by line. But we just discussed, okay, when the code looks like this, number one control reaches here, and then all of these lines are skipped for once. Control reaches here, all of these lines are skipped. You directly reach this, and now the sum function is called. So the control reaches here, you do a for loop. Then you come out of the for loop, you log answer of 1. Then again the function is called, the control reaches here. So synchronous doesn't necessarily mean that you can't have breaks like this. You can't go from one code block to another. What it means is, okay, this is actually a very bad sort of a definition, executed line by line. When we see asynchronous code, we will immediately understand what is synchronous and how is it different from asynchronous. But whatever code we have seen, for loops, if else statements, while loops, we didn't discuss them, but hopefully you Google after the class. All of these are synchronous code, which basically means एक बार में एक line चल रही है. During at one time, one line is running and they're being executed in order like this. So control which is here, for loop here, so on and so forth. That is what synchronous code is. कोई definition पढ़ने का फायदा नहीं हुआ. No real benefit of learning the definition because it's just code that we've been writing until now. Let's understand asynchronous operations. Asynchronous. Synchronous, what does the statement tell you? क्या synchronization है? Line 1 runs, line 2 runs, line 3 runs. For loop चल गया, function call हो गया. Line 5, 7 runs, line 8 runs, line 9 runs. Return हो गया. Line 30 runs, line 31 runs, line 32 runs. Function call हो गया. Line 7 runs, line 9 runs. Whenever this is happening, it is synchronous code. But real life backends, real life computer science programs are not always for loops. They are not always while loops. They are not always if-else statements. A lot of times, the backend code that you're writing or even the front-end code that you're writing involves IO heavy operations. This is where I have to understand the first jargon for the day. IO or input output heavy operations. DSA problem when you're solving, you never deal with IO heavy operations. You deal with CPU heavy operations. What is a for loop? A CPU heavy operation. If a for loop is running from 1 to a million, the CPU is constantly occupied running the for loop. It is running really fast, but it is running the for loop. The CPU is occupied running the for loop. A lot of times, you have things to do in a program where the CPU is not required. Might sound like very dumb thing. CPU is the machine. Why do I need the machine? You're saying here there are tasks to do in a program where there is no CPU involved. Yes. Let's see what those tasks are. They are called IO bound or IO heavy operations. IO heavy operations refer to tasks in a computer or things that a computer needs to do or a program needs to do. Refers to tasks in a computer program that involve a lot of data transfer between program and external system or devices. That involve a lot of data transfer between programs and external systems or devices. What is a good example of this? Let me think of a simple one. A simple one is reading a file from a program. I repeat. Let's say you're on a Mac machine. I'm on a Mac machine. Let me quickly create a Mac machine over here. You could be on a Windows machine, doesn't matter. Here you might write some JavaScript code, right? We understand JavaScript code now. We can write for loops. We can write if-else statements. Let's say the JavaScript code that you're writing, if it has for loops, while loops, if-elses, it is synchronous code. But if this JavaScript program is supposed to read another file, मान लो, there is another file in your machine called a.csv. Let's say there is a CSV file, or a TXT file, or a binary file, or an Excel file, or a PPT file. You might have to write the code to read a CSV file, clean up the CSV file, write back to the CSV file. You might have a program like this. There are a lot of compression programs. When you download a compression program, it cleans up space on your machine. So that program, the cleanup program or the compression program, is supposed to delete files from your machine. It's supposed to find the files that are idle and let's say delete them. Or it might have to read the files in a variable over here. Do something with that. Make it smaller, compress the file, and then write back to the file. So a lot of times, Not in DSA. You will never see a DSA statement that says read from a file and then clean it up. You might see a DSA problem that says given you already have a CSV file in a variable, then clean it up. That is a standard DSA problem. There is no reading or writing of another file that is happening. But if in a program of yours you have to read a file, that becomes an asynchronous or a IO heavy operation. That becomes a IO heavy operation because what does IO mean? It means input output. कि मतलब मेरे control से परे है. I don't know how long it will take for this file to get read. I don't know how long it will take for this file to get read. Here you have to understand another concept of a operating system or an OS or kernels. Do you think if you write a random program or if you download a random program on your machine, it should have the power to read files from your computer? Let's say I download a random file, some random website download a file, I click on it. What is the file? It is effectively a lot of code that is written. Should that file by default have access to read from your file system? Ideally not. Should that file have access to write from your file system? Ideally not. Otherwise, I will create such a file, put it in the chat, you will download, you will click, you will double click. It will delete everything from your machine. It will fill your machine with random garbage. So whenever you download program from the internet, or if you are writing any program yourself, there are permissions that your OS might ask. Your operating system Windows will give you a pop-up. Okay, are you sure you trust this program? Only if you click on allow, will it be allowed to read and write programs, read and write other files, so on and so forth. The same is true for this index.js file. ये जो index.js file है, when you run this file on your Mac machine, when you run this command node index.js, unless node has access to everything on your machine, this file should not be allowed to read the other file. Generally, when you install Node.js on your machine, you do give it access to do whatever on your machine because the code base of Node.js is the Node.js runtime is very well audited. सबको पता है कुछ अजीब नहीं हुआ है. So you in a very trustless fashion download the Java virtual machine on your machine, or you download the Rust compiler, or you download the Go compiler, or you download Node.js, or you download Bun. क्योंकि आपको पता है कुछ अच्छा ही है वहाँ पे. When you run this program, the program might be a cleanup program whose job is to find a file or read a file, do something with it, clean up the file a little bit, decrease the space, rewrite to the file. When you read a file, you actually ask the operating system, क्या ये file मुझे read करने दोगे please? A program can't simply read from the file system. उसको ऑपरेटिंग सिस्टम को पूछना पड़ता है. It needs to ask the operating system, can I read the file? The operating system checks कि हाँ, this node program does have access to read the file. The operating system checks, is this a valid file or not? It checks, is this file being read by someone else? Is this file being written to by someone else? Is this file logged right now by a different program? And after all of those checks happen, is when the OS will, return you the file that you asked for. अगर आपको file read करनी है, you can simply ask the operating system, and the operating system will, in its own time, could be 1 millisecond, could be 10 milliseconds, could be 100 milliseconds, could be 1 second. In its own time, return you the contents of the file. This is called a IO heavy task. Why? क्योंकि all you can do is ask the operating system कि मुझे file दे दो. If it returns you the file in 100 milliseconds, you are stuck here for 100 milliseconds, and your CPU is not really being used. You are not running a for loop. You are not running a while loop. You are not doing anything. You have simply called one function, read function. Let's say there's a read function that reads a specific file. You simply called that function with a path to a file. आपने simply इस function को call कर दिया. इसके बाद this asks the operating system for the contents of the file, and then this Node.js, this index.js is just waiting. Operating system पे depend करेगा कि वो कब लौटाएगा. If it returns in 200 milliseconds, the JavaScript thread isn't doing anything. अगर मान लो इसके बाद एक for loop होता, there is a for loop after this from whatever 1 to 20,000, the control will never reach the for loop. Even though it would have been nice if it did. अगर क्योंकि फाइल रीडिंग तो उसने ऑपरेटिंग सिस्टम से पूछ लिया, राइट? इट आस्क्ड द ऑपरेटिंग सिस्टम क्या ये फाइल रीड कर दोगे प्लीज. नाउ व्हाइल द ऑपरेटिंग सिस्टम इज फिगरिंग आउट कि डज index.js, does node.js have access to read the file, is this file logged, while it is doing these checks, wouldn't it be nice if the control reached to this for loop, you were able to run your for loop logic, and whenever the file was read, the control reached back over here somehow. I repeat, wouldn't it be nice जब ये asynchronous function call हो रही है, when there is this asynchronous function call, the JavaScript runtime, the JavaScript thread could do other things. The only reason this question comes up is because this is an asynchronous function call जहाँ पे the JavaScript, this Node.js binary can only ask the operating system कि भाई मुझे फाइल दे दो. And now it is completely dependent on the operating system कि वो कब लौटाएगा. हो सकता है 10 सेकंड बाद लौटाए. The operating system might return the contents after 10 seconds. Now for those 10 seconds, wouldn't it be nice if the control reaches the for loop after that, the while loop after that, and does a bunch of other things. And whenever this file is read, the control can somehow reach back here. Now you might have a lot of questions. Kirat, अगर if this happens, कि I fire off the event to read, and then I do a for loop, and then I do a while loop, and then the file is read, so the control reaches back here. Then the for loop run again, the while loop will run again. That is a good question. We'll come to answer that question very soon. But do we understand what is an IO heavy operation? Examples of IO heavy operations include reading a file. We'll understand what it means to start a clock, but starting a clock. A good example of this is, let's say you want to print 1, 2, 3, 4, 5 like this on the console, like a countdown. How can you write the code to print a countdown over here from 1, 2, 3, 4, 5, 6, 7 like that? We'll come to that. How that is done. That's also an asynchronous operation. What are HTTP requests? What are database requests? We'll understand when we reach there. Abhi no, these are also asynchronous operations. But the one that we immediately intuitively understand is reading a file. Let's try to write some code that does an IO heavy operation. I repeat. Ab we're going to write some code that does a IO heavy operation. Abhi tak we've only done CPU heavy tasks. This code is going to do the very first IO heavy task. You can't do this task here, or can you? You unfortunately can't do this task here. You will have to install Node.js locally, unfortunately. So if you don't have Node.js locally, then I think you're sort of out of luck today. Let me see if I can find something else. JSFiddle might work. Actually, JSFiddle might work. You can also go to jsfiddle.net. I might be speaking too soon, I say, because this is like HTML, CSS. Yeah, this might not work either, unfortunately. You will need to have Node.js installed locally. For those of you who don't, try the same things later on when you have Node.js installed. For the people who do, open a new folder on your machine. and put a JS file over there. So let me create a new folder called class 3 because this is the third class of the cohort. And let me open this in. I'm opening this in Cursor. You can open this in Visual Studio Code or whatever your IDE of choice is. What is an IDE? You should go through the warming up videos and you will understand. What IDE do I use these days? I use Cursor most of the times. So let me open Cursor locally on my machine. Let's try to see what this asynchronous code is that we're trying to write. What was the goal of the class? The goal of the class was to understand what is asynchronous code. We're trying to write our very first asynchronous function call right now. Let me open a new empty folder over here. Let me close all the AI agent windows and let me open the file system over here, add a new index.js file. What did I do? I created a new index.js file locally. This everyone should be able to do. But if you want to run this, you have to have Node.js installed locally, which I'm assuming a lot of you do. Most of you do, some of you don't. Let's look at the code. Kya code hai that was written over here? This is fresh syntax for us. We have written if else for loop, variable creations, things like these, functions. We have not yet seen this code. What exactly is this code? Let's try to understand. Go back to the slides. You will see something that says we're going to introduce imports and requires next. A require statement lets you import functions exported from other files or modules. In Node.js, in Go, in Rust, everywhere, a lot of developers have written a lot of good code in libraries. A lot of developers have written a lot of code in various libraries. If you want to call a function from their library, you have to import their library like this. For example, what does the first line of code here say? It says const fs, a variable name that I wanted to create, equal to require the fs module, the file system module. What is this? This is a module come package that someone has created called fs or file system. And what does this line of code do? This line of code gets the code of that file system module in this variable. When I wrote for loop, while loop, तब तो मुझे कुछ import नहीं करना था. Yes, because they are part of the standard JavaScript syntax. You don't have to import anything for that. But this fs.readFileSync function, this function right here, is unfortunately exported from a separate module. So you have to import that module to your file. In my case, the file is index.js. This is an internal package. I repeat, this is an internal package, which means it comes shipped with the Node.js runtime. It comes shipped with the Node.js runtime. आप Node.js install करोगे, उसके साथ ही आएगा. That is not true for a lot of external packages. We'll come to later what external packages are. But if you've heard of Mongoose, if you've heard of Express, if you've heard of Hono, these are external packages. We'll come to them later. This is an internal package. I imported it. I wrote this line of code which called the function fs.readFileSync. fs.readFileSync, which says, what does the function name sort of tell us? क्या इस file को read करने की कोशिश करो. Try to read the contents of this file. And this is the encoding in which the contents of the file are present. I don't have a a.txt over here right now. Let me add it. Let me add a a.txt over here. And in it, let me write, some random UTF-8 code. Hi there. For those of you who don't know what UTF-8 is, the 3 classes we have covered. Basically, when you are calling this read file function, इसको नहीं पता कि ये English में लिखा हुआ है. It doesn't. How does it know कि this code is English code or is this binary code or is this Spanish code? Is this Russian code? Is this some random encoding or language? Which is why you have to tell it. क्या इसके अंदर ना standard जो English की UTF-8 encoding होती है, that covers a lot of languages, Latin, Spanish, English. उसमें कोड लिखा है. We are telling it. Yeah, this is the encoding in which you should read the file contents. They are written in UTF-8. For those of you who don't understand, Web3 class, we have covered encoding. Same. When I log in, what do you expect? You expect to see the contents of the file. So if I run this code now, which the people who do have Node.js should be able to, I pressed Command J or Control J to open the terminal. I can run node index.js here to actually run this program. What will it do? Read the contents of this file, log them on the screen. If I run this, I see hi there has been printed. Beautiful. The code seems to do what it was supposed to do. It was able to read the file, log it to the screen. But notice the function name says something. fs.readFileSync. Read file synchronously. अभी थोड़ी देर पहले हकीरत said कि examples of IO heavy tasks, asynchronous tasks, tasks that are not CPU bound is reading a file. Reading a file should be an asynchronous task. Asynchronous का मतलब क्या है कि while the file is being read, I'm not using the CPU to do something. The CPU is free. The JavaScript thread is not doing anything. वो वेला बैठा है. It is sitting and waiting for the operating system to respond, which can respond in its own time. That is what an asynchronous operation is. But here I called fs.readFile synchronously. So I am doing an asynchronous operation synchronously over here, which basically means कि fs.readFileSync will ask the operating system क्या ये file read करना, and until the operating system responds, the JavaScript thread will be stuck over here. It will not move after this. If there was a for loop that was trying to calculate something important right after, this for loop will not run until the file is read. So if this file reading took 300 milliseconds, for those 300 milliseconds we did nothing. Even though it would have been nice if you could have jumped to the for loop, done the for loop, and then read the contents and logged. I repeat, it would have been better. अगर हम किसी तरीके से, we could have fired off an event to the operating system. Please read the file. While the operating system is filling it out, I could have moved on to the for loop, run the for loop. Whenever the operating system returns the file contents, I could have come back here and logged the contents. This would have been better because I would have used time more optimally. If you are supposed to boil water on one side and do dishes and wash your clothes, will you go to wash your clothes and just stare at them while they're washing? Or will you go, turn on the machine, go to the gas, turn on the boiling water, go to the dishes, start to do them, come back to the washing machine, check is it done, it is not done, okay, come back to the water, is it boiled, it is boiled, turn off the gas, go back to the dishes, start to do the dishes, keep moving between the washing machine and the dishes. This is more optimal way to do 3 tasks, right? Similarly, here we are supposed to do 2 tasks. But Here we are just waiting for the operating system. It's like staring at the washing machine while it is, if you know for a fact the washing machine is going to take 10 minutes. There is no point staring at it. It makes sense to move your JavaScript thread to do something else. In this case, to run a for loop over here. Doing the dishes is a CPU intensive task. You are constantly involved doing the dishes. Washing machine is an asynchronous task. You have to turn it on and then the washing machine will do its thing. It's like asking the operating system to do something, operating system will do its thing. Boiling water is an asynchronous task. You will turn on the boil, you can move on and do other things. You can come back to it later. So there are two asynchronous tasks here, one synchronous task. But even though this is an asynchronous task, we are not calling it asynchronously just yet. We are calling it synchronously. So do we understand how this is ideally an asynchronous task, but we are doing it synchronously for some reasons? We'll get to what those reasons are and how we can make it better eventually. Do we understand asynchronous operations and how we are doing an asynchronous operation synchronously right now? But very soon we will see how can we somehow parallelize this. It's not actually parallelizing, but it's actually me, just staring at the washing machine while it is washing, whatever, my clothes, and then coming back to the dishes after the washing is done. Do we understand asynchronous operations? We'll understand them more when we understand HTTP servers eventually and databases, things like these. 94% is good. I will proceed. 92 ho gaya, 91 ho gaya, but I think most people have voted. 91 is good. I will proceed. Come back to this video. There are other videos that we have done that cover the same thing. I'll post those videos. Alright, this is the first code. If you understand this code, you can probably understand this code as well. What does this code do? Read a.txt, log it. Read b.txt, log it. Here again, can you see an unoptimality? Can you see how this code is unoptimal? I am firing off a read file request, but then waiting for it to respond. Or respond kar. Then I am firing off the read file to request. It's like I have two washing machines, but I'm putting clothes in one, turning it on and staring at it. And when it finishes, I take the clothes out. Then I go to the other one, put the other sets of clothes in and start. Then I can run these sort of parallelly. Parallel is the wrong word, but if it ideally makes sense for me to go to the first washing machine, turn it on, go to the second machine, turn it on, and then wait. Then when the first one is done, go back to it, take the clothes, go back to it and take back the clothes. That's the ideal way to do it. This code is reading the first file. पूरी read हो गई operating system में 2 minute बाद होता है. Operating system returned you after 2 minutes, let's say, it was a very big file. Or the operating system was busy doing other things. Then for those 2 minutes you never really ask the operating system to do the second thing. It would be nice if I can fire these requests one after the other, and I don't care when the operating system returns. That is out of my control. वो तो operating system depend करता है. How long it takes to return. So hopefully you understand IO heavy operations, how are they different from synchronous operations. A simple comparison of IO bound tasks versus CPU bound tasks. CPU bound tasks are operations that are limited by the speed and power of the CPU. These require significant significant computation and processing power, meaning that the performance bottleneck is the CPU itself. This is a CPU intensive task. If I'm on a very fast, Razer CPU by Mac, then this for loop might run faster because the CPU is more optimal, can run for loops. this for loop will run slower. But every second when this runs, every millisecond when this is running, it is using the CPU to compute something. That is what this for loop is doing. There is no IO bound task here. There is only one or many CPU bound tasks here. Declaring a variable is a CPU heavy task. Running a for loop is a CPU heavy task. Logging is a CPU heavy task. A real world example of CPU nested tasks are running for 3 miles. Your length task for loop is. I'm on a very old machine. This for loop will be fast. Razer CPU by Mac. Then this for loop might run faster because the CPU is more optimal. Can run for loops faster. If I'm on a very old machine, this for loop will run slower. But every second when this runs, every millisecond when this is running, it is using the CPU to compute something. That is what this for loop is doing. There is no IO bound task here. There is only one or many CPU bound tasks here. Declaring a variable is a CPU heavy task. Running a for loop is a CPU heavy task. Logging is a CPU heavy task. A real world example of CPU nested tasks are running for 3 miles. Your length rate छोड़ दो. Once I was doing a mile at my college campus and learning Node.js, and a very weird comparison came to my head. This is that comparison, but it's a very bad comparison. So ignore it. I up to my head. This is that comparison, but it's a very bad comparison. So comparison came to my head. This is that comparison, but it's a very bad comparison. So ignore it. IO bound tasks are operations that are limited by the CPU's IO capabilities, such as its disk IO. You might have heard of, when you deploy your databases, you're very worried about disk IO. When you are talking to a database, you're worried about network input output. How much, bytes per second, kilobytes per second can I get from this network? How much is the disk IO? How many bytes I can read and write from the file system of my machine? These are things that limit कि आप कितनी jaldi file read कर सकते हो. If you're reading a file, even the CPU is sort of involved, the JavaScript thread is not involved in reading the file. The read file is being done by the operating system on a separate thread. The JavaScript thread can ideally do other things. In this case, the read file function that you see is a asynchronous function call or an IO bound function call. These tasks spend most of their time waiting for the IO to complete. These tasks spend most of their time waiting for the input output to complete, which means they're waiting for the operating system to return something. Or many other examples of HTTP requests, database requests that we come to later. Real world examples, I hope you understand. If you're supposed to do 3 things: boil some water, do some laundry, and send packages via mail. Would you do them one after the other? मतलब पहले I'll start to boil the water, keep staring at it, wait for it to finish, and then once it is done, then start the laundry, look at all the clothes, keep staring at them. Once they are done, then move on to going, to send the package. Or would you context switch between them? Would you? और अपने context को यहाँ से यहाँ बीच में लेके जाओगे ना? That's ideally what you would do. You would start the water, चालू हो गया, move on to the start कर दिया, चालू हो गया, move on to going to the first package वाली जगह, quickly delivering the package coming back, seeing the bottle white, so on and so forth. You will parallelize these. Sort of parallelize. That is the wrong word in JavaScript, which is why I'm avoiding the word parallelize. I can come to later why I'm very heavily avoiding the word parallelize in JavaScript. The real word is concurrency. You're running these things concurrently. Would you start all 3 of these requests together and wait for them to finish? The one that finishes first gets catered to first. The third example seems, like 2 and 3 में ज़्यादा फर्क नहीं है, but 3 seems like a good one. 5 of this, move on to, whatever. Give your package and, whichever one finishes first, you tend to that one first. This code that we have written is similar to doing these things sequentially, even though reading, boiling water can take the 10 seconds. For those 10 seconds, you could do other things. You're still not doing it. You are stuck over here waiting for the operating system to tell you, किसके contents मिल रहे हैं. Hopefully that analogy sort of, works and we understand that analogy. Before we proceed and we provide or we understand how to write or convert this synchronous function call to asynchronous, before we do that, we need to understand something else called functional arguments. We need to understand something called functional arguments. Concept is simple but can get harder to digest. So let me start with a simple example. Ignore all the code that we had written. We understand this code. Let me delete it for now. A simple example is, let's say I describe a function called sum and another function called divide. Actually, subtract is a better one for now. Return. I've written 2 functions. The 2 functions do what they're supposed to do. I can call them. I can log their outputs, so on and so forth. Now let's say I could write another function called do arithmetic, whose job is to take 2 numbers as an input, a comma b, and take what to do. Subtract करना है या add करना है. So a third argument, take something like this. If seen here, written here yet, 2 functions that have the meat of the logic. कि sum करना है, subtract करना है. I've written a first function. Let's say I force you कि आप sum को सीधा call नहीं कर सकते. You cannot call sum or sum directly. You can only call the do arithmetic function, which can call sum if need be, which can call sum if need be. So I call do arithmetic. If I call it with sum as an input, then the sum function is called with a product. Okay, functions are what are called first class citizens, which basically means they're like any other variable. Just like I can pass a as a variable to, I can write let a equal to 1 over here. Called use the concept of functional arguments. But one thing to know in JavaScript at least is, okay, functions are what are called first class citizens, which basically means they're like any other variable. Just like, one can be a variable, I can write let a equal to 1 over here. And I can pass a around as variables here. Just like I can pass a as a variable to a function, I can pass, b as a variable to a function. I can also pass a function as an argument to a function. This is very, hard for beginners, slightly hard for beginners, but एक बार समझने की कोशिश करते हैं. Rather than passing a string as the third thing, I can pass what I want this function to do as the function only. कि यार do arithmetic, ये sum function को कॉल कर देना. Please call the sum function. I मैं variable elements जो साथ में आपको पास just this duplicated का नाम अब fn बन गया है until this function body becomes this sum variable. That is all that it means. It is a little complicated to digest, but really what is happening is the third argument that you're passing, the fn variable becomes equivalent to that function. It's like a function का नाम अब fn बन गया है until this function body ends. When I pass 1 over here, a becomes 1, right? B becomes 2, right? So similarly, fn becomes this sum function. And if I call fn, it is equivalent to me calling the sum function. जब ये function call हो रहा है, when the first function call is happening, sum is being passed in f. But 55 I'm calling it. With if करोगे तो बहुत काम multiply, subtract, divide, star function divide हो गया. But there is a fifth function that I have written. Do operation that takes AB and literally the function operation as an input. क्या sum करना है? तो over here I'm going to do operation with 1, 2 and this whole function is 1 and 2, so it will get to as an argument. You understand this? Because it's not easy to digest the first time, but maybe code and really writing asynchronous code. Actual me is understanding this, 96% understanding this, because it's not easy to digest the first time, but maybe I'm a great teacher, or you guys are already very smart, probably that. Function arguments we understand, so we move on to. We come back to actually, we don't move on to, we come back to asynchronous code arguments. Number of first example, this whole function. So इसके अंदर OP becomes this whole function. So when I call OP, it is equivalent to me calling the sum function with whatever inputs were passed here, which is 1 and 2, so it will return 3, we will log 3 on the screen. We can do more examples of this, but these are very forced examples. We will really see this in action in asynchronous code. So can we move on to asynchronous code? Do we understand function as a first class citizen? Just like you can pass a string, a number, a boolean to a function, you can also pass another function to a function as an argument. You can pass a function to a function as an argument, which is why they're called functional arguments. They're called functional arguments. Very surprising, 95 people are understanding this, 96% understanding this, because it's not easy to digest the first time, but maybe I'm a great teacher, or you guys are already very smart, probably that. Functional arguments we understand, so we move on to. We come back to actually, we don't move on to, we come back to asynchronous code and really writing asynchronous code. Actual में asynchronous code लिखेंगे. Until now, we were doing a asynchronous function call synchronously. पागल हैं हम तो ये सारे मिलके हमें what were we doing? We are doing something not good. Some other YouTuber picked it up and said कि देखो हाँ ये क्या हुआ है. Which is bad. YouTube पे जहाँ पे मैंने गलती से डाला doing something not great. We were doing a asynchronous function call synchronously. पागल हैं हम तो ये सारे मिलके हमें what were we doing? We are doing something not great. We were calling an asynchronous function synchronously. वो नाम ही लिखा है. In fact, एक बार मैंने वीडियो बना दी थी YouTube पे जहाँ पे मैंने गलती से डाल दिया तो some other YouTuber picked it up and said कि देखो हाँ ये क्या हुआ है. Which is bad. To be fair, this is not something you should do because of performance. Okay? While the file is being read, आप फाइल को रीड कर रहे हो बैठ के, तो your JavaScript thread can do other things, run a for loop, while loop, whatever logic you have right after. So why should you make your thread stare at the washing machine while the file is being read, while the operating system is doing its thing? So question is, if here read file is an asynchronous function here, we understand it's an IO bound operation. How can I call it asynchronously here? Here comes another function in FS. ये FS library, general external libraries इतनी cool होती हैं कि you press dot, it shows you everything that you have here. And notice there are two functions here, read file and read file sync. We were using the unoptimal one, गंदा one. YouTube पे गाली पड़ेगी ये डालोगे तो this is the better. और interview में गाली पड़ेगी कि why have you written read file synchronously when it is clearly an asynchronous operation because it depends on the operating system, not the current process. And similarly, read file is going to call this, read this file asynchronously. वाजिबा. तो मतलब इतना चेंज करना था. All I had to do was call read file and not read file sync. Not really, not exactly. क्यों? क्योंकि what did we say? Okay, let's say I write some beautiful code after this CPU bound code. I am writing CPU bound code. इसके बाद मैं CPU वाला code लिख दिया, which is a very big for loop जहाँ पे कुछ है. Which let's say supposed to find the sum from 1 to 100,000. Let s equal to 0, s plus equal to I, and then console.log s. Now, here, are you telling me that read file is being called asynchronously? So this will get fired, and then the thread will do the whatever for loop and do its thing log s. And अगर ऐसा हो रहा होता, if this is a really asynchronous function call, and the JavaScript thread can move on to do other things, so how does the JavaScript thread know कि मुझे इसको skip करना है? Ideally, the JavaScript thread needs to skip this, right? ये तो आ रहा है operating system से. The JavaScript thread needs to move on to this for loop, while loop, whatever logic exists after that, and then come back to this and this line of code. अब JavaScript thread इतना smart तो नहीं है कि वो समझ पाए कि JavaScript thread can't understand कि यार these 4 lines I have to skip, क्योंकि ये तो contents को use कर रहे हैं, which is currently being read from the operating system. This is an asynchronous function call. I need to directly move on here to the CPU intensive task. Unfortunately, the code isn't as similar, but we have just learned the concept of functional arguments. हमने क्या पढ़ा अभी? कि when you are calling a function, you can also pass it another function as an input. What if such a syntax was valid? कि यार a.txt read करनी है, UTF-8 में read करनी है, और जब read हो जाए, whenever it is read, then this function को please call कर देना. Please call this function whenever the file is read. It will get a little confusing. Don't worry, we will understand it very soon. But if let's say the code look like this, so at least does the original problem go away? कि यार read this file in UTF-8 and whenever it is read, operating system, please इसको call कर देना. Please call this function when the file is read. So these 3 lines are automatically skipped. a.txt, we just call the read file function and we pass the third argument as another function. I can describe this function अलग से also, जैसे हम पहले करते हैं. हमने sum अलग से लिखा था. Let me write this अलग से. Let me call this function file read callback. Let me call this function file read callback. this index को we wrote a while back. What did I write back? A while back. Some function अलग से लिखा था, and then do something and we were passing some as the third argument. But that was synchronous code. Somewhere in the do operation function, we were automatically and clearly calling जो भी third argument pass हो रहा है. This function was called, and then इसके अंदर we were calling the sum function. fs.read file, whoever has written fs.read file, which as you can see is an internal library. Whoever has written is probably the maintainer of Node.js or maintainer of Chrome, whoever wrote V8. In this case, it's the maintainer of Node.js. उसने ऐसा कहा कि यार functional arguments exist. It's not necessary कि आपने अगर एक function argument दिया है, if you're given a function argument, it needs to be called this function. It's the same as me starting my washing machine and telling my washing machine after 5 minutes do a very loud beep. While my washing machine is washing, I am going to do other things. While the operating system is actually reading the contents of the file, figuring out my permissions, I am doing other CPU intensive tasks of finding the sum from 0 to 100,000. And whenever it is done reading a file, it will call this third function as an argument. Do we understand why function arguments make sense heavy for asynchronous functions? Asynchronous functions के लिए these function arguments, or what are also known as callbacks, call back इस function को बाद में call कर देना. That is what the callback is. That is why they make a lot of sense for asynchronous function calls. क्या जब ये चीज हो जाए तब इस function को call कर देना? Because if we don't do it, do you remember how the code looked like before? It looked like this. And here again the problem is, how does the Node.js runtime know कि इन तीनों lines को skip करके this is the code that I have to actually run, and whenever the file is read, then contents variable will come and then these two I have to store. Versus if I write this code, then the Node.js runtime understands कि हाँ I have to call this function whenever I'm done reading the file. The thread moves on to the next thing where contents variable इसके बाद कहीं नहीं दिखा है. Okay? Don't make sense heavy for asynchronous functions. Asynchronous functions के लिए these function arguments, or what are also known as callbacks, call back इस function को बाद में call कर देना. That is like before. It looked like this. And here again the problem is, how does the Node.js runtime know कि इन तीनों lines को skip करके this is the code that I have to actually run, and whenever the file is read, then contents variable will come and then these two I have to store. Versus if I write this code, then the Node.js runtime understands कि हाँ I have to call this function whenever I'm done reading the file. The thread moves on to the next thing where contents variable इसके बाद कहीं नहीं दिखा है. Only when the function is called do you get access to the contents function, the contents of the file that you can log over here. This code will run. It will work as you expect, which is it will fire off the read file event and it will start to do its own thing here, and then it will log the sum of 1 to 100. The common question you might ask here is, Akirat, ये error क्या है? Shouldn't it look like this? Shouldn't it look like this? File read callback है. Whenever the operating system is done reading the file, it should simply call this function with the contents of the file. Why are you writing error comma contents? Because it's not necessary कि ये file वहाँ exist भी करती है. It's not necessary the file exists. It's not necessary the Node.js has permissions to read from your file. It's not necessary the file is available right now. It might be that the file is very big to be read, and hence there are a lot of things that can go wrong. If things go wrong, the Node.js runtime will tell you that in this ERR variable. This ERR variable will tell you what went wrong. If everything went fine, ERR will become null, and you will get the actual contents of the file here. Another question is, why is it ERR first and then contents? Why is it not something like this? अगर सब सही है, then contents. If something goes wrong, then error. Now these are just commonly known as error first callbacks. If you've ever done Golang, you understand what these are. These are every function in Golang returns two things. The first thing that it returns is an error, and the second thing that it returns is the actual thing that you need. Just a pattern of error first callbacks. Whoever wrote fs.read file really liked the pattern, really liked the error first callback pattern, and hence he wrote the code like this. कि यार मैं जब operating system मुझे लौटा देगा, when the operating system will tell me the file has been read, I will call this function first with an error variable, second with the contents variable. तो अगर कुछ error है मैं यहाँ दूंगा. If there is no error, I will tell you null over here. I will give you the contents of the file. So what do you expect to be logged in this case? Logically सोचते हैं, what do we expect to be logged in this case? Does the contents of the file get logged first, and then s variable gets logged, or does the s variable get logged first and then the contents get logged? Trick question, logical question, puzzle for you guys. This is the code that I have written. I am first doing fs.read file. पहले मैं file को read कर रहा हूँ. Then I am doing this for loop and printing s. So will s come first? Will contents come first? Or will it be vague? Will it be vague? क्या ऐसा होगा कि कभी-कभी s will print first, कभी-कभी contents will print first? Let's do a poll and let's see how smart the audience is today. What is the poll? Which one of these three things would happen? Let me quickly create the poll. The first thing is s gets printed first, then content. Third thing is this code on my page seems like the better answer over here. First. Vague seems like the better option. You don't know how quickly this callback will get called. It might get called immediately. It might take a really long time to get called. So, this s variable, this for loop might get interrupted in the middle if this function callback happens. So it seems like vague is the right answer. 38% say vague. 17% say contents, comma s, and then 45% the majority is smart with or already knows this. So I would say smart. I think logically you should arrive at vague is the right answer. But the actual answer is first s gets printed and then contents. Why is that? For that we have to go to the next slide. We'll go to that slide very soon, which is the architecture for JavaScript asynchronous code. अभी इसको नहीं देखते हैं. But yes, s gets printed first, then this comes. Why? Because the way the JavaScript runtime, specifically the JavaScript asynchronous runtime, asynchronous architecture works is, if there is a callback that is being called, if there is the operating system telling you कि file read हो गई, it can't interrupt the current CPU task जो चल रहा है. अगर CPU is busy doing a task, it will keep doing that task, irrespective of the operating system waiting to call this callback. मतलब, if I make this really, let's see does this work, and were the people in the audience correct? First s, then contents. That is true. First s gets printed, then the contents of the file get printed. The second question is, another very good question is, if I make this like a really big calculation, now this calculation might take 5 seconds. You know for a fact in 5 seconds तो file read हो जाएगी. File read does not take more than 5 seconds. The file can be read in 1 second at max. It's a very small file. So again, the common thought that comes is, yeah, this will take 5 seconds. At the first second itself, the operating system should call this callback, and then after the first second, contents should get logged, and then for the next 4 seconds, this for loop should run whatever. But no, you will still notice, if the JavaScript thread is busy doing the CPU task, why is it not printing anything? Because it is busy doing this for loop right now. If it is busy doing this for loop, it does not matter that the operating system is ready to call this callback. It does not matter if the operating system is ready to call this callback. The CPU task will keep on happening. After it prints, the CPU task becomes free. The JavaScript thread becomes free. इसके बाद ये अब तो मेरे पास कुछ नहीं करना. Then it will check क्या कोई callback call हुआ है? Is there some callback waiting? And if it is, then it will call that callback. So if the CPU is busy somewhere, if the JavaScript thread technically is busy somewhere, it will remain busy, and no asynchronous callback can interrupted. It cannot be interrupted by asynchronous callback. We will see this in action very soon. Before that, let me introduce another asynchronous operation. What if I tell you, yaar, print 1 on the screen? Let's do something similar, a simpler asynchronous. asynchronous function call. If I say क्या print, let's have two variables a equal to 1, b equal to 2. I say क्या पहले print a comma b, a console.log b. After you printed these, wait for 1 second and then print their sum. Let's say this is a question that I ask you. Okay, print two variables a b. Wait for 1 second, then print their sum. Is this program doing what it says? It doesn't. It will immediately print a b and their sum, a b and their sum. What code can I write here such that it waits for 1 second? Hakikat, you can write something like this. Write an empty for loop that, hopefully, this is long enough to run for maybe 900 milliseconds, maybe 2000 milliseconds, I don't know. But there's some delay. There's some artificial delay I added between printing a b and, whatever. There's some. If I run this again, notice 1, 2 is printed, and after not 1 second, but 3, 4, 5, 6 seconds, 3 is printed. You can make this exactly 1 second also by doing something like this. Now, this syntax some of you might not understand, but bear with me for a second. Let current or before time equal to date dot now. If let current time equal to date dot now. If current time minus before time is greater than equal to 1000, click. Now the code that you see on the screen will exactly wait for 1 second, very close to 1 second, before the for loop, breaks. What does break do? It basically stops the for loop right there and moves the control out. For loops can stop when this condition is not met at some point, or they can also be stopped by this break statement. So the code that I've written might be a little hard to digest, but basically it gets the current timestamp here in some variable over here, and then inside the for loop, as time passes by, this current time variable will keep on increasing as the for loop is progressing, and there will be a difference between the time that we tracked before, let's say 9:34 p.m. and then the current time, which will 9:34:01, 9:34:02, 9:34:03 बढ़ता जाएगा. When the difference between them is greater than or equal to 1000 milliseconds or 1 second is when we can break the for loop. So this code would exactly after 1 second or almost exactly after 1 second print a b and then there's some after almost exactly 1 second. If I run this, notice 1 second के बाद मोटा-मोटा 3 gets printed. So here I have accomplished what I initially wanted to accomplish, which was print a b, wait for 1 second, print the sum. But doesn't this smell like an asynchronous operation? Doesn't this smell like an asynchronous operation? क्यों? क्योंकि कुछ नहीं करना 1 सेकंड के लिए. For 1 second you are supposed to do nothing. Might as well run a different for loop. अब इसके बाद अगर कुछ कोड होता, whatever. Let's say there's some code right after that is a very expensive CPU task for loop that you want to run. Wouldn't it be nice कि जब तक 1 सेकंड तक वेट हो रहा है, उस 1 सेकंड तक हम ये दूसरा for loop रन कर लें? Because during this 1 second you're literally supposed to do nothing, but you are forcefully making the CPU do something. आप CPU से forcefully कुछ नहीं करा रहे हो. You're telling the CPU to literally do nothing and just extend. Wouldn't it be nice if over here you could tell the operating system यार 1 सेकंड बाद मेरा कॉल बैक कॉल कर देना. You could tell the operating system कि यार after 1000 milliseconds or 1 second, call this callback function. And in this callback function, I can log a plus b. I can log a plus b in this callback function. And इसके बाद there's a for loop, expensive for loop that is running. This set timeout is another asynchronous function call you can do that will start the clock somewhere else. There's a separate thread that's taking care of the clock. 1 second हो गया कि नहीं, and your thread can move on to doing other things. It's the same thing as reading a file asynchronously. What was I doing before this? I was waiting for 1 second synchronously. It's also commonly known as a busy wait. कि मैं CPU को busy रखते रखते wait कर रहा हूँ. I am forcefully making the CPU busy in a for loop. Versus here, I'm just starting the clock somewhere else and moving to doing other things in the CPU. CPU busy as reading a file asynchronously. There's a separate thread that's taking care of the clock. 1 second हो गया कि नहीं. This set timeout is another asynchronous function call you can do that will start the clock somewhere else. There's a separate thread that's taking care of the clock. 1 second हो गया कि नहीं, and your thread can move on to doing other things. It's the same thing as reading a file asynchronously. What was I doing before this? I was waiting for 1 second synchronously. It's also commonly known as a busy wait. कि मैं CPU को busy रखते रखते wait कर रहा हूँ. I am forcefully making the CPU busy in a for loop. Versus here, I'm just starting the clock somewhere else and moving to doing other things in the CPU. CPU अलग चीजें कर रहा है. That's what set timeout is. So set timeout is another example of an asynchronous function call, and hopefully you understand why it makes sense for it to be asynchronous, because during that 1 second, now the Node.js runtime can run other things. Versus जो मैंने पहले कोड लिखा, the code that I did before, there the function, I couldn't run any logic after that, which was bad. I was busy waiting using a forceful for loop over here. hopefully you understand clocks. If you remember a while back, that is what I mentioned here as well. Examples of IO heavy operations, reading a file and starting a clock, which is exactly what we did over here. We started a clock, but we delegated the tracking of 1 second to something else. We were not ourselves tracking for 1 second. Now, I mean, let's do a poll. Do we understand set timeout and general things that we have discussed until now, which is asynchronous versus synchronous, busy waiting समझ आ गया, forceful for loop, whatever, do something versus an asynchronous operation to do the same thing. ये थोड़ा कम समझ आया, ये थोड़ा ऊपर ऊपर से निकल गया. Which is why we will discuss this again. I'm sure there's 1 or 2 common questions that I have missed. Well, I'm going to answer some questions. It's only 80%, which is not great for such a initial class. So, looking at Q&A now, specific questions related to what I have said here, I would love to answer. Opening Q&A now. Another 5 minutes, I'll do open Q&A, move to slides. Why await not to work in fs.read file? Don't know why. Questions, it's only 80%, which is not great for such a initial class. So, looking at Q&A now, specific questions related to what I have said here, I would love to answer. Opening Q&A now. Another 5 minutes, I'll do open Q&A, we'll move back to slides. Why await not to work in fs.read file? Don't know why. How to know that function is async or sync? What do we call the function with async but take callback instead of dot? Then yeah, so a lot of these functions, set timeout, fs.read file, were written before promises were a thing. Promises became a thing when I was doing my very first GSOC, because I remember clearly the promises were taught to be by my very first maintainer back in 2016. So they probably were introduced in 2014. fs.read file is older. They don't want to change it, which is why fs.read file is not promisified. It is whatever. It uses a callback, but there is an fs/promises library that you can use that has promisified versions of fs.read file. Does prompt also act like a synchronous function call? Now, that's a beautiful question. I think prompt also is ideally an asynchronous function call that is forced to be synchronous. So let's see how it works. Prompt will probably let the user ask for a variable. Prompt message. What do you want A to be? Let A equal to this thing, and then whatever. Let B equal to the second prompt. Now both of these should be asynchronous ideally, but this prompt function. It's sort of written synchronously. Let's look at it. Great question, by the way. Beautiful exercise. कि जो prompt function है, which basically is a function that will take input from you here. I don't know what the syntax is. Prompt. What am I missing? Oh, is this not available in Node.js? I think it's read line in Node.js, but you get the idea. Prompt exists in the browser and not in Node.js, which is why we did not see it. But let's say I write, prompt here. What is your name? Directly, prompt me to answer this. I will answer this. And ideally, while I am answering this, the thread should do other things, but it will, from what I can see right now, block the thread. So there should be a promisified version of this if it does exist. I don't think it does. We can Google it. Let's Google. Is there a async/promisified version of prompt? The prompt. Yes, there are several ways to make it asynchronous. There are libraries like there is a prompt.js library, prompt async library that will let you run prompt asynchronously. But the prompt function that we generally write is not asynchronous, unfortunately. I'm even not sure if this is correct. I also think this is incorrect. I don't think this will actually do what it proposes it will do, because the thread will sort of get stuck over here. So I think this is like AI. This is like classic example of AI slop, where it is telling us something which is 99% I'm sure wrong, because it is creating an asynchronous function which under the hood is still using a synchronous function call, which would change nothing. So basically, yes, it should ideally be asynchronous. It is usually synchronous over here, and you use synchronously just like fs.read file sync. But there is a library prompt async. So let's see what these guys are doing to actually hopefully make it async. The example that these guys gave us was incorrect. I wouldn't say it makes prompt asynchronous, but we can read through the code base of this and see what these guys are doing. This looks actually correct, but I can't read its code over here. So let me quickly try to read the code here. If it is readable, it is not. It is not readable. Let's see. Prompt function. This looks right to me. The real question is, what is this unpatched function equal to prompt of this thing? Yeah, this might be asynchronous. I could be wrong. It's slightly ugly code that is written. This seems like this actually might be using a callback based approach and promisifying it. So this library might actually make prompt. By callbacks very soon. And someone asked a very nice long question. Basant naam hai, sorry. Basant. So how do I copy this? So I'll start with Basant and I'll recap a few things and we will proceed. This is the code that Basant has pasted. He says const fs equal to require fs. And I mean, you're saying yahan pe return ho raha hai, which which is expected because a.txt does not exist for you or something like that. Okay. And then this code you're saying it is outputting. So beautiful question, Basant. on Windows machines, or even here, let's see, you might see this error from time to time. He has written simple code over here, read file sync /a.txt, which is a.txt file here, UTF-8. It should work. It does work for me. It might not work on some operating systems for many reasons. For example, if I do this, अगर मैं एक folder पीछे चला जाऊं, and then if I run node class 3 /index.js, do you think this will run? No, because आप इसको class 3 folder से run कर रहे हो. So it will start to find a.txt in the class 3 folder. That is, what might be happening for you as well. So if I run this, I receive the same error, k file does not exist. क्योंकि मेरे root folder में a.txt नहीं है. It is in class 2 library. Will probably not work in this case. क्योंकि इसमें भी dir name will be, when you do a path.join_dir name this thing, actually this also will probably not work in this case. क्योंकि इसमें भी dir name will become the root directory and there's no a.txt here. So for you, the reason you are seeing this, कि some operating systems में, some terminals में, you can't simply write dots and then /a.txt. In some operating systems, some bash version that you're using, some terminal that you're using, you have to write the full path. In my terminal, thankfully I did not have to write the full path, which is why you're seeing directory. So if I have the class called, but path.join is a better way to do it, because the path library will sort of, this also works, but if you galti se write this versus here you are not using the full path, and in some operating systems you do need the full path. Let's create a stopwatch. Let's create a stopwatch. What is a stopwatch supposed to do? It is supposed to print 1 after 1 second, 2 after 2 seconds, 3 after 3 seconds. Here comes another function called set. इंटरवल, क्या ये एक फंक्शन है जिसको मैं नाम दे रहा हूं कॉल बैक. प्लीज कॉल इट एवरी 1 सेकेंड. देयर इज अ function called callback. You can name this whatever you want. You can name this Hakirat. You can name this interval callback. You can name this callback. Call this function every 1 second. I am telling someone else कि यार हर एक सेकंड में इस फंक्शन को प्लीज कॉल करते रहना. While I am free to do other things like a for loop or whatever I want to do, अलग से I can do other things while someone else keeps calling the callback function every 1 second. And what I can do here is simply print a variable, something like this. Let counter equal to 0, console.log counter, counter equal to counter plus 1. So what will this do? It will print 0 the first second, 1 the second second, 2 the third second, watch in free for that 1 second. If I want, I can write a for loop after this that does, whatever, finds the sum from 1 to 100. को call करने का time आ गया. It's time to call the callback function. It's time to call the callback function. बैठा है इस कोने में and every 1 second is telling me या callback को call करने का time आ गया. It's time to call the callback function. It's time to call the callback function. But I am not necessarily maintaining that clock using a busy wait or a for loop. I am simply, doing whatever. आप लोगों के दिमाग में वो आया क्या? भूल भुलैया वाला बंदा जब मैंने बोला ऐसे बैठा है, ये वाला. The thing can do, I can do, I is less than whatever, the thread will be busy running a busy loop, for loop, again and again, and figuring out 1 second हो गया, 2 second हो गया, 3 second हो गया. Versus, in this case, someone else is maintaining the clock, you are free to do other things as you want. One again, trick question for you guys. Let's say this is a very long for loop, where I'm doing nothing, just finding the sum from 1 to this very big number. Print होगा. And after 10 seconds, let's say this gets printed, or does something else happen? What did we discuss a while back? When you call an asynchronous function, give it a function to call back. यार जब एक अभी मैंने इसको क्या बोला है? This function what is it supposed to do? Every 1 second it's supposed to tell me कि callback को call करने का time आ गया है. But if I am busy doing my thing, I will not listen to him. मुझे फर्क नहीं पड़ता वो log. I don't care if I will still do my thing of running the for loop, and I don't care if 1 callback is piled up or 2 callbacks are piled up or 3 callbacks are piled up. So if I run this again, notice 1 second हो गया, but nothing got logged. Only after the whole thing ran for a really long time is when the clock started. So if I run this again, now 1 second हो गया, 2 second हो गया, 3 second हो गया, but nothing is getting logged. Why? Because the operating system is telling me कि यार callback को call करने का time आ गया after every second. But I am busy doing my own thing. It's like if I have 5 washing machines that I have started, but I am now busy dancing. So I will dance irrespective of the 5 washing machines beeping after every कि भाई हो गया है, हो गया है, हो गया है. I will come to them when I'm done dancing. And similarly here, when I'm done running the for loop, don't you guys laugh? You haven't seen me dance yet. When I'm running the for loop, it doesn't matter if someone else is telling me कि callback call करो, callback call करो. All the callback number 1 will get called. I'll print count and increase it. Callback number 2, 50 जो line में लगे हुए हैं, all those prints will happen together because all of those callbacks are waiting. Which takes us to the last section for the day, which is the architecture for asynchronous JavaScript code. इससे थोड़ा ज़्यादा clear होगा कि why exactly it behaves this way. Why is it that I keep on dancing even when 3 washing machines are waiting for my attention? The answer is how the JavaScript runtime was written, specifically the async runtime was written. Whoever wrote this decided कि उनको ऐसे लिखना था. They could have decided to write it a different way. कि if the clock interrupts, then the callback should get called and you should return over here. But the way they have written it is, if the CPU is busy doing something, it doesn't matter how many people are standing in line, telling the CPU to do other things, telling the CPU to call a callback, the CPU will keep doing its own thing. Eventually, line 14 पे जाकर CPU will get free when the CPU can move on to callback 1, callback 2, callback 3. Let's see this in action though. Let's copy this code. And the code that you see over here is very well visualized over here. कि अगर ये code run होता है, some asynchronous code runs, how does it move across the JavaScript stack? The asynchronous JavaScript stack. So asynchronous JavaScript stack. Notice the things on the right. There is a call stack section. ये हर language में mostly होता है. Most languages have stacks. There are 2 types of languages, stack-based languages and register-based languages. Most languages we deal with are stack-based languages. So they have this concept of a call stack. If you've done compiler design, you might have seen this. इसका काम ये होता है कि as functions are getting called, they keep on getting pushed to this call stack. So if I don't write any asynchronous code, make them simple synchronous code.
In this section, we will take a look behind the scenes of JavaScript and learn how the language actually works. So throughout this section, as an introduction to this theory section, I want to start with a very cool and very high-level overview about the JavaScript language, just so you get a first overview of most of the things that we need to learn in order to eventually master JavaScript. And this is going to be a long lecture, so get ready for a crazy ride. And I want to start by coming back to that first definition that I gave you on JavaScript, where I told you that JavaScript is a high-level, object-oriented, multi-paradigm programming language. Now, this is of course 100% correct, but it's also really just the surface, the tip of the iceberg. So what about this definition? JavaScript is a high-level, prototype-based, object-oriented, multi-paradigm, interpreted, or just-in-time compiled, dynamic, single-threaded, garbage-collected programming language with first-class functions and a non-blocking event loop concurrency model. Wait, what? Is this some kind of joke? Well, yeah, it kind of is, actually. I just packed as much information as possible about JavaScript into one unreadable sentence just for fun. But besides fun, this also gives us a great opportunity to unpack all of this in order to get a first peek into all the stuff that we're going to learn about JavaScript throughout the course. And this is not to intimidate you. It's really not. I just want you to get the big picture before really getting started, and also introduce some topics that are just good to know. Because getting the big picture before diving deep is, in my opinion, an amazing learning technique. So with that being said, let's unpack this now a little bit. So these are the 9 JavaScript topics that we're briefly going to talk about in this lecture, slightly reordered. And starting with the high-level part, as you might already know, every program that runs on your computer needs some hardware resources, such as memory and the CPU, to do its work. Now, there are low-level languages, such as C, where you have to manually manage these resources. For example, asking the computer for memory to create a new variable. On the other side, you have high-level languages, such as JavaScript and Python, where we do not have to manage resources at all, because these languages have so-called abstractions that take all of the work away from us. This makes the language easier to learn and to use, but the downside is that programs will never be as fast or as optimized as, for example, C programs. Now, one of Scott and Fuhr, or memory, called machine code. This step is necessary in every single programming language because no one writes machine code manually. In the case of JavaScript, this happens inside the JavaScript engine. Now, one of the things that makes JavaScript so popular is the fact that it's a multi-paradigm language. In programming, a paradigm is an approach and an overall mindset of structuring your code, which will ultimately direct the coding style and technique in a project that uses a certain paradigm. And this definition still sounds kind of abstract, but don't worry, it will become more clear as we move on. Now, 3 popular paradigms are procedural, object-oriented, and functional programming. So procedural programming is what we've been doing so far, which is basically just organizing the code in a very linear way, and then with some functions in between. Now about object-oriented programming and functional programming, I will talk about them in a second. Also, we can classify paradigms as imperative or as declarative, but again, more on that later. Now, many languages are only procedural, or only object-oriented, or only functional, but JavaScript does all of it. So it's really flexible and versatile, and so we can do really whatever we want with it. It's our choice. We can use whatever paradigm we want. And in this course, I will show you how to use all of them. So, about the object-oriented nature of JavaScript, it is a prototype-based, object-oriented approach. Now, what does that mean? Well, first, almost everything in JavaScript is an object, except for primitive values such as numbers, strings, etc. But arrays, for example, are just objects, and we already saw that in practice, right? Now, have you ever wondered why we can create an array and then use the push method on it, for example? Well, it's because of prototypal inheritance. Basically, we create arrays from an array blueprint, which is like a template, and this is called the prototype. This prototype contains all the array methods, and the arrays that we create in our code then inherit the methods from the blueprint, so that we can use them on the arrays. And this, what I just explained to you, is actually a huge oversimplification, which might still sound confusing, and that's the reason why there is a whole section on object-oriented programming with JavaScript later in the course. But since this is a big overview lecture, I wanted to first introduce this topic right here. Next up, JavaScript is a language with first-class functions, which simply means that functions are treated just as regular variables. So we can pass functions into other functions, and we can even return functions from functions. And this is extremely powerful, because it allows us to use a lot of powerful techniques, and also allows for functional programming, which is one of the paradigms that we just talked about before. And in fact, we have already used the power of first-class functions without knowing that they are called first-class functions. So remember this piece of code that we wrote for closing the modal window that we built before. So right here, we passed the close modal function into the addEventListener function as if it was just a regular variable, right? And actually, not all languages have first-class functions, but JavaScript has, and it is amazing. Believe me, it's really, really helpful. Next, I said that JavaScript is a dynamic language, and dynamic actually means dynamic, actually a huge oversimplification, which might still sound confusing, and that's the reason why there is a whole section on object-oriented programming with JavaScript later in the course. But since this is a big overview lecture, I wanted to first introduce this topic right here. Next up, JavaScript is a language with first-class functions, which simply means that functions are treated just as regular variables. So we can pass functions into other functions, and we can even return functions from functions. And this is extremely powerful, because it allows us to use a lot of... Okay, that's cool, but why do we need that thing that they are called first-class functions? So remember this piece of code that we wrote for closing the modal window that we built before. So right here, we passed the close modal function into the addEventListener function as if it was just a regular variable, right? And actually, not all languages have first-class functions, but JavaScript has, and it is amazing. Believe me, it's really, really helpful. Next, I said that JavaScript is a dynamic language, and dynamic actually means dynamically typed. So as we've already seen, in JavaScript, we don't assign data types to variables. Instead, they only became known when the JavaScript engine executes our code. Also, the type of variables can easily be changed as we reassign variables. And this is basically what dynamically typed means. Now, there's a lot of controversy if this is good or bad, but this is just how it works. Now, the same is not true for most other programming languages, where we have to manually assign types to variables. And this then usually prevents bugs from happening, which is the reason why many people say that JavaScript should be a strongly typed language as well. And if you yourself want to use JavaScript with types, then you can always look into TypeScript. But anyway, let's now finally talk about the single thread and the non-blocking event loop concurrency model. Now, this is a really complex topic, and probably the most complex one of the whole course, which is why it's kind of at the end of the course. And therefore, I'm not going to go into specifics here just yet, but instead I will just define some things here. First, what actually is a concurrency model? Well, it's just a fancy term that means how the JavaScript engine handles multiple tasks happening at the same time. Okay, that's cool, but why do we need that? Well, because JavaScript itself runs in one single thread, which means that it can only do one thing at a time. And therefore, we need a way of handling multiple things happening at the same time. And by the way, in computing, a thread is like a set of instructions that is executed in the computer's CPU. So basically, the thread is where our code is actually executed in a machine's processor. Alright, but what if there's a long-running task, like fetching data from a remote server? Well, it sounds like that would block the single thread where the code is running, right? But of course, we don't want that. What we want is so-called non-blocking behavior. And how do we achieve that? Well, by using a so-called event loop. The event loop takes long-running tasks, executes them in the background, and then puts them back in the main thread once they are finished. And this is, in a nutshell, JavaScript's non-blocking event loop concurrency model with a single thread. It sounds like a mouthful for sure, but in the end, it really just compresses to this. Just keep in mind that, again, this is a huge oversimplification that we will come back to. Alright, and this actually rounds up this overview lecture. I know there was a ton of stuff to take in, but I hope that you still learned a thing or two here. So I talked about the JavaScript engine in the last lecture, but what is that engine actually? And what is a JavaScript runtime? Also, how is JavaScript code translated to machine code? So that's just some of the topics that we talked about in the last video, and so now let's find out how they work in this lecture. So a JavaScript engine is simply a computer program that executes JavaScript code. There are a lot of steps involved in doing that, but
Have you ever wondered what actually makes your JavaScript code run, whether it's in your browser, on a server, or even in a brand new app? Most people think JavaScript is just a language, but here's the twist. JavaScript by itself can't do anything until it's inside a runtime environment, and that's where the real magic and the real differences begin. But wait, here's something you might not know. The way your code runs in Chrome is not the same as how it runs in Node.js, Dino, or Bun. In fact, the runtime you choose can completely change your app's speed, security, and even what features you can use. So let me ask, have you always assumed JavaScript just works everywhere? What if the how and where matter more than you think? Stick around, because by the end of this video, you'll know exactly what a JavaScript runtime environment is, how it works, and how to pick the right one for your next project, whether you're building a website, a server, or something totally new. Let's break it down. A JavaScript runtime environment is like the stage where your code performs. JavaScript itself is just the script. It needs a runtime to bring it to life. This environment provides all the tools, libraries, and infrastructure your code needs to actually do things like talk to the network, access files, or update a web page. At the heart of every runtime is the JavaScript engine. Think of this as the brain. It reads your code and makes it run. Chrome and Node.js use the V8 engine, Firefox uses SpiderMonkey, and Safari uses JavaScript core. Each engine interprets and executes your code, and some even optimize it for speed using something called just-in-time JIT compilation. But the runtime isn't just an engine. It also gives you special powers called APIs. In browsers, APIs let you change the web page, handle clicks, or fetch data from the internet. On servers, APIs let you read files, handle network requests, and more. So, what are the core components of JavaScript runtime environment? Here's how the pieces fit together. JavaScript engine, the interpreter and executor of your code. It manages the call stack, which tracks what's running, and the memory heap, where your data lives. APIs, extra tools for interacting with the outside world, like the DOM in browsers or file systems in Node.js. Callback queue and microtask. Queue. Think of these as waiting rooms for code that needs to run after something else finishes, like after a timer or a network request.
Yes, engine, which contain just basically the call stack and the call stack and the heap. APIs, DOM API, set timers, fetch. Now the event loop. It's basically as the micro tax queue, callback queue.
Event loop, the conductor, making sure everything runs in the right order. It checks if the main thread is free, then moves tasks from the queues to be executed. This setup lets JavaScript handle lots of things at once, even though it's single-threaded. That's why your web page can stay responsive while fetching data in the background. Here's a short snippet of code that will help us visualize the runtime in action. We first console log 1, then we console log 2 inside a timeout, then inside a promise resolve, we console log 3, and finally we console log 4. At first glance, you might think it logs 1, 2, 3, 4 in that order. But what you actually get is 1, 4, 3,
There's queue and back queue, callback. Promise. This is promise.
Strange, right? Let's break it down. This is our components. We will not think about the heap for now. Let's walk through how asynchronous JavaScript works under the hood. First, we have console log 1. This is a synchronous call. It gets pushed to the call stack, runs immediately, and prints 1. Next, we see set timeout. Now, set timeout is not handled by the JavaScript engine itself. Instead, it's handed off to the web API environment provided by the browser. That means the callback inside set timeout gets scheduled to run later. If the timeout value is 0 milliseconds, it will still be sent to the callback queue, but only after everything else finishes. If the timeout value is something like 100 milliseconds, it will wait 100 milliseconds before going into the callback queue. If the timeout value is 0 milliseconds, it will still be sent to the callback queue, but only after everything else finishes. If the timeout value is something like 100 milliseconds, it will wait 100 milliseconds before going into the callback queue. Then we have promise resolve then. This creates a microtask, it goes into the microtask queue, and it waits to run right after the main synchronous code finishes. After that, we have console log 4, which runs immediately and prints 4. At this point, the call stack is empty, so the event loop kicks in. Here's what the event loop does. First, it looks at the microtask queue. The promises dot then callback is sitting there, so it gets pushed onto the call stack, runs, and prints 3. Next, the event loop checks the callback queue. Where the is loop that we have console, it goes into the microtask queue, and it waits to run right after the main synchronous code finishes. After that, we have console log 4, which runs immediately and prints 4. At this point, the call stack is empty, so the event loop kicks in. Here's what the event loop does. First, it looks at the microtask queue. The promises dot then callback is sitting there, so it gets pushed onto the call stack, runs, and prints 3. Next, the event loop checks the callback queue, where the set timeout callback is now waiting. It gets moved to the call stack, runs, and finally prints 2. So even though set timeout had a 0 delay, it still had to wait until the microtasks were finished. This is how asynchronous JavaScript works behind the scenes. Even a 0 delay timeout must wait for the microtasks to complete first. Now let's look at the main environments where JavaScript runs. First, we have the browser. This is the original home for JavaScript. It gives you web APIs to interact with web pages and user events. but it keeps you in a sandbox for security, so there's no direct file access here. Next, we have Node.js. This is the server-side powerhouse. It's built on the V8 engine and is great for building web servers and APIs. Thanks to its non-blocking, event-driven design, it's fast and efficient. Plus, it has a massive ecosystem through NPM. Then there's Deno. It's the new kid on the block, made by the creator of Node.js. Deno is secure by default, supports TypeScript out of the box, and uses a decentralized approach to managing dependencies. Finally, we have Bun. It's built for speed. Bun is an all-in-one toolkit with a super fast engine. It's designed to be a drop-in replacement for Node.js with better performance. So, next time you write JavaScript, don't just think about the code, think about the world your code lives in. The right runtime is your secret weapon. If you want to watch similar content, please subscribe to the channel. Turn on notifications to get notified when I release a new video. If you found this helpful, share this video, like, and comment your ideas below. Thank you so much for watching, and I'll see you.
Topic in JavaScript, but when we zoom out, it's just a tiny component within the JavaScript runtime. We also have the call stack, we have web APIs, we have the task queue, microtask queue, and then eventually the event loop. Well, to be a little more technically accurate here, we actually have the JavaScript engine, in which we have the call stack, and then also the memory heap, but to keep my slides a little organized, I'll just be showing the call stack here. All these components together allow us to use asynchronous tasks in a non-blocking way in JavaScript. And this is important because JavaScript itself is single-threaded. We're only working with a single call stack. So the call stack manages the execution of our program. So if we have the following script, we first have console log 1. So a new execution context is created, pushed onto the call stack, which is then evaluated in logs 1. Then we have console log 2, same story. Execution context is created, pushed onto the call stack, is evaluated in logs 2. Then on line 14, we invoke another function, the log 3 and 4. And within this function body, we invoke yet another function, log 3. And within log 3, we invoke another function, the console log 3. Eventually logs 3. Then on the second line within the log 3 and 4 function body, we console log 4. 4 gets logged, and now the log 3 and 4 execution context is popped off the call stack as well. Now something important to remember here again is that JavaScript can handle a single task at a time. So if we, for example, have this long running task in which we have a pretty heavy computation, it takes a while before JavaScript can continue with the rest of our program. So the console log long task done is only logged after a couple seconds. And this is not what we want, because in the meantime, our entire program is frozen. So we want to avoid these long running tasks. But in a real-life application, we often have to use these long-running tasks, like maybe a network request or anything based on user input, timers. So what happens then? Like, is our entire call stack just blocked until we get the data back? No, because we're actually using web APIs in those cases. And web APIs provide a set of interfaces that allow us to interact with the browser's features. This includes functionality that we often use, like the document object model, fetch, set timeouts, and so many more. The browser is a very powerful platform with a lot of features. Some of these features are required, like the rendering engine or the networking stack. But we also have access to some cooler ones, like device ones, sensors, cameras, geolocation, and so on. Okay, cool, but what does this have to do with long-running tasks? Well, some of these web APIs allow us to offload long-running tasks to the browser. So when we invoke such an API, we're kind of just initiating that offloading. And web APIs that expose these asynchronous capabilities are either callback-based or promise-based. So first, let's focus on the callback-based APIs. And I'm just going to use the geolocation API because it's fun. I could have used any other callback-based API. But let's say that we want to get the user's location. And for this, we can use the synchronous capabilities are either callback-based or promise-based. So first, let's focus on the callback-based APIs, and I'm just going to use the geolocation API because it's fun. I could have used any other callback-based API, but let's say that we want to get the user's location. And for this, we can use the getCurrentPosition method exposed by the geolocation API. And this receives two callbacks. First, we have the success callback in case everything goes well and the user allows us to get the location and we actually get it from the browser, or the error callback in case anything goes wrong. So let's see what happens when we actually use this in our script. So first, the getCurrentPosition invocation gets added to the call stack. However, this is just to register those callbacks and initiate that async task. After doing that, it can get popped off the call stack immediately, so it doesn't wait for any data. Now in the background, the browser starts some kind of process that eventually shows the user a pop-up. Now, of course, we don't know when the user is going to interact with this pop-up, but that's not a problem because this is not happening on the call stack, so our entire website is still responsive in case other tasks need to run instead. Now, finally, the user clicks on allow. So the API receives the data from the browser and uses the success callback to handle this result. However, it can't just push that callback back onto the call stack. This could disrupt an already running task and just create very unpredictable behavior. So instead, the callback gets pushed to the task queue, which is also called the callback queue for this exact reason. The task queue holds web API callbacks and event handlers to be able to get executed at some point later in the future. And this is where we finally get to the event loop. It's the event loop's responsibility to check if the call stack is empty. And if that's the case, so if nothing is running, it then gets the first available task from the task queue and moves this to the call stack where it's executed. So now finally, we handle the results and the user's location is logged to the console. Another very popular callback-based web API is setTimeout. And setTimeout also receives a callback and a delay. So let's see how that works. So first we encounter a setTimeout. And this again gets added to the call stack, but all it does again is register that callback and also the delay with the timers API. And in the background, the browser will actually handle that timer. Then we have another setTimeout, and again, it registers the callback and the delay. Now our timers are still running, and we have a console log end of script. This just gets added to the call stack and logs end of script, nothing asynchronous here. Now after 100 milliseconds, the browser's like, hey, 100 milliseconds expired. So now the callback moves onto the task queue. There's nothing on the call stack right now, so this moves onto the call stack where eventually it logs 100 milliseconds. Now 2000 milliseconds are up. Again, same story. The callback is pushed onto the task queue. Call stack is empty, so it moves onto the call stack where it logs 2000 milliseconds. So it's just very important to remember that when you have a set timeout and a delay, it's not the delay until it gets moved onto the call stack. No, it's the delay until it gets moved to the task queue. So this means that the delay that we specify might not actually be the delay to execution. Because if the call stack was still very full with other tasks and this could run for many more seconds, the callback would still have to wait in the task queue until the call stack is empty. So just something to keep in mind. So long story short, the callbacks provided by web APIs are pushed onto the task queue when the asynchronous task completes. So what about the promise-based ones? If you haven't checked out my promises video yet, I highly recommend to watch it because I'll just assume some basic promise knowledge while explaining this entire flow. Whenever we work with promises, we're working with the microtask queue. The microtask queue is a special queue dedicated to then catch finally callbacks, a function body execution after await, the queue microtask callback, and the new mutation observer callback. So only those callbacks or those function body parts get pushed onto the microtask queue. So it's very specific. However, the event loop prioritizes the microtask queue. Whenever we work with promises, we're working with the microtask queue. The microtask queue is a special queue dedicated to then catch finally callbacks, a function body execution after await, the queue microtask callback, and the new mutation observer callback. So only those callbacks or those function body parts get pushed onto the microtask queue. So it's very specific. However, the event loop prioritizes the microtask queue. So whenever the call stack is empty, the event loop first ensures that the microtask queue is entirely empty. So it gets all the tasks from the microtask queue, moves them onto the call stack where they get executed, and only then will it move to the task queue. And after each task in the task queue, it again checks the microtask queue. And a popular promise-based web API is fetch. So let's see what happens behind the scenes when we invoke fetch. So whenever we call fetch, it's added to the call stack. This is just responsible for creating a promise object, which by default is pending. The result is undefined, and we don't have any promise reactions just yet. It also initiates the background network request that's handled by the browser. Then we move on to the next line with the then handler, and this creates a promise reaction record where we have res console log res. The server still hasn't responded, by the way, but we get to line 4. So there we have a synchronous console log end of script. So now end of script is logged to the console. And then finally, the server returns some data. So now the promise data set is fulfilled. The promise result is now the response object with the data that we got from the server, and the promise reaction handler is now also pushed to the microtask queue, right? Because it's a then callback, and that gets pushed to the microtask queue. The call stack is empty, so the event loop checks the microtask queue, moves this to the call stack where it eventually logs the result that we got from the server. Something to keep in mind with microtasks is that a microtask can also schedule another microtask. And this means that the event loop is just constantly handling the microtask, and it can never actually get to the task queue. It would just have to wait indefinitely. So we're kind of creating an infinite loop, an infinite microtask loop, freezing our entire program. I believe in Node you can set like max tick depth or something like that, which prevents this exact thing from happening. But just make sure that you don't accidentally end up doing that. And we can also promisify a callback-based API. So for example, we can rep the get current position with a new promise constructor. And for the success callback and the error callback, we just pass resolve and reject. So this can be a pretty nice solution just to improve the readability within your code base a bit. All right, a little quiz to see if you kind of understand it. So we have a promise resolve with a then handler. We have a set timeout. We have a queue microtab. In which we have another queue microtask, and then we have a console log 5. It's up to you to see what gets logged. So pause the video now and let's see if you got it. Right. And the right answer is 51342. So let's see why. First, we have the promise resolve, and this just creates a new promise object that's instantly resolved. Then on the next line, you have the then handler. The promise is already resolved, so in the background, it does create that promise reaction, but the handler is immediately pushed to the microtask queue. Then we have set timeout, which is responsible for initiating the timer. So the callback and the delay get passed to the API, and in the background, the browser starts some sort of timer. Then we have queue microtask. So the call is added to the call stack, and this queues that callback to the microtask queue. Then we have the synchronous console log 5, so this gets pushed to the call stack and logs 5. And in the meantime, the 10 milliseconds of task callback. And within this queue is entirely empty. It's eventually logged to hand it off to the browser. The logs 2. So now we have 51342. So let's just recap what we've covered so far. So JavaScript is single-threaded. So this queue is entirely empty before moving on to the task queue. And after handling each task from the task queue, the event loop again checks the microtask queue to ensure that nothing has been added in the meantime. You often come across asynchronous JavaScript, and if you aren't entirely sure why things execute a certain way,
Hello everyone, thanks for coming to the sidetrack. It's awesome. loop, and what the heck is the event loop? As in the event loop inside JavaScript. So first up, as he said, I work for Andyet, which is an awesome little dev shop slash product company in the US. Look us up if you need help with real-time stuff. That's what we're good at. So about 18 months ago, I'm a paid professional JavaScript developer. I thought to myself, how does JavaScript actually work? And I wasn't entirely sure. I'd heard V8 as a term, Chrome's runtime, didn't really know what that meant, what that did. I'd heard things like single-threaded, obviously I'm using callbacks, how do callbacks work? So I kind of started a journey of reading and research and experimenting in the browser, which basically started like this, right? I kind of was like, JavaScript, what are you? And it's like, I'm a single-threaded non-blocking asynchronous concurrent language. All right, that's, yeah, cool. I have a call stack, an event loop, a callback queue, and some other APIs and stuff. Right, I did not do a computer science degree. These words, they're words. So, I heard of V8 and the various runtimes in different browsers, so I looked at V8 and said, do you have a call stack, an event loop, a callback queue, and some other APIs and stuff? I have a call stack and a heap. I don't know what those other things are. Okay, interesting. So, basically 18 months pass. We're 18 months later now, and I think I get this. And so this is what I want to share with you today. So hopefully this will be useful if you're relatively new to JavaScript, help you understand why JavaScript is so weird when you compare it to other languages you might have used, why callbacks are a thing, which cause us hell but are required, and also if you're an experienced JavaScript developer, hopefully give you some kind of fresh insights into how the runtime that you're using every day works so that you can kind of think about it a little better. So if we look at the JavaScript runtime itself, like V8, for example, which is the runtime inside Chrome, this is a simplified view, really, of what the JavaScript runtime is. It's a heap, which is, we don't need to worry about that, it's kind of boring, it's just where memory allocation happens. And then there's the call stack, which is where your stack frames are and all that kind of stuff. But if you clone the V8 code base and grep for things like set timeout or DOM or XML HTTP request, they're not in there. They don't exist in V8, which was kind of a surprise to me, right? Set timeout's one of those first things you use in JavaScript when you start thinking about async stuff, and it's not in the V8 source. Interesting. So over this 18 months of discussion,
Not really a good talk. Yeah.
But essentially, executing JavaScript code is what an engine does. Now, every browser has its own JavaScript engine, but probably the most well-known engine is Google's V8. The V8 engine powers Google Chrome, but also Node.js, which is that JavaScript runtime that we talked about in the beginning of the course, so the one that we can use to build server-side applications with JavaScript, so outside of any browser. And of course, all the other browsers have their own JavaScript engines, which you can look up online if you're interested. Anyway, it's quite easy to understand what an engine is, but what's most important is to actually understand its components and how it works. So any JavaScript engine always contains a call stack and a heap. The call stack is where our code is actually executed using something called execution context. Then the heap is an unstructured memory pool which stores all the objects that our application needs. Alright, so with this look at the engine, we have answered where our code is executed. But now the question is how the code is compiled to machine code, so that it actually can be executed afterwards. Well, let's find out. But first, we need to make a quick computer science side note here and talk about the difference between compilation and interpretation. So in the last lecture, we learned that the computer's processor only understands zeros and ones, and that therefore, every single computer program ultimately needs to be converted into this machine code. And this can happen using compilation or interpretation. So in compilation, the entire source code is converted into machine code at once, and this machine code is then written into a portable file that can be executed on any computer. So we have two different steps here. First, the machine code is built, and then it is executed in the CPU, so in the processor. And the execution can happen way after the compilation, of course. For example, any application that you're using on your computer right now has been compiled before, and you're now executing it way after its compilation. Now, on the other hand, in interpretation, there is an interpreter which runs through the source code and executes it line by line. So here we do not have the same two steps as before. Instead, the code is read and executed all at the same time. Of course, the happens not with what then you would do next step and fix in time compilation. This approach basically compiles the entire code into machine code at once and then executes it right away. So we still have the two steps of regular ahead of time compilation, but there is no portable file to execute, and the execution happens immediately after compilation. And this is perfect for JavaScript, as it's really a lot faster than just executing code line by line. Now, I skimmed over some details here, but this is really all you need to know. Anyway, let's now understand how this works in the particular case of JavaScript. So as a piece of JavaScript code enters the engine, the first step is to parse the code, which essentially means to read the code. During the parsing process, the code is parsed into a data structure called the abstract syntax tree, or AST. This works by first splitting up each line of code into pieces that are meaningful to the language, like the const or function keywords, and then saving all these pieces into the tree in a structured way. This step also checks if there are any syntax errors, and the resulting tree will later be used to generate the machine code. Now let's say we have a
passing AST in semantic analysis AST with Google
very simple program. All it does is to declare a variable like this. And this is what the AST for just this one line of code looks like. So we have a variable declaration, which should be a constant with the name x and the value of 23. And besides that, there is a lot of other stuff here, as you can see. So just imagine what it would look like for a large, real application. And of course, you don't need to know what an AST looks like. This is just for curiosity, okay? Now, sometimes I get asked if this tree has anything to do with the DOM tree. And the answer is a very clear no. So this tree has absolutely nothing to do with the DOM. It is not related in any way. It's just a representation of our entire code inside the engine. Anyway, the next step is compilation, which takes the generated AST and compiles it into machine code, just as we learned in the previous slide. This machine code then gets executed right away, because remember, modern JavaScript engine use just-in-time compilation. And remember, execution happens in the JavaScript engine's call stack, but we will dig deeper into this in the next lecture. Alright, so far so good. We have our code running, so we can finish here, right? Well, not so fast, because modern JavaScript engines actually have some pretty clever optimization strategies. What they do is to create a very unoptimized version of machine code in the beginning, just so that it can start executing as fast as possible. Then, in the background, this code is being optimized and recompiled during the already running program execution. And this can be done multiple times, and after each optimization, the unoptimized code is simply swapped for the new, more optimized code without ever stopping execution, of course. And this process is what makes modern engines, such as V8, so fast. And all this parsing, compilation, and optimization happens in some special threads inside the engine that we cannot access from our code. So completely separate from the main thread that is basically running in the call stack, executing our own code. Now, different engines implement this in slightly different ways, but in a nutshell, this is what modern just-in-time compilation looks like for JavaScript. And the next time someone tells you JavaScript is an interpreted language, you just show them this slide so that they can learn how it really works. Alright, so we looked at the JavaScript engine and how it works behind the scenes in quite some detail. Now, to round off this lecture, let's also take a look at what a JavaScript runtime is, and in particular, the most common one, which is the browser. And by doing this, we can get the bigger picture of how all the pieces fit together when we use JavaScript. And so this is a really important slide. So, we can imagine a JavaScript runtime as a big box, or a big container, which includes all the things that we need in order to use JavaScript, in this case, in the browser. And the heart of any JavaScript runtime is always a JavaScript engine. So exactly the one we've been talking about. That's why it makes sense to talk about engines and runtimes together. Without an engine, there is no runtime, and there is no JavaScript at all. However, the engine alone is not enough. In order to work properly, we also need access to the web APIs. And we talked about web APIs before, remember? So that's everything related to the DOM, or timers, or even the console.log that we use all the time. So essentially, web APIs are functionalities provided to the engine, but which are actually not part of the JavaScript language itself. JavaScript simply gets access to these APIs through the global window object. But it still makes sense that the web APIs are also part of the runtime, because, again, a runtime is just like a box that contains all the JavaScript-related stuff that we need. Next, a typical JavaScript runtime also includes a so-called callback queue. This is a data structure that contains all the callback functions that are ready to be executed. For example, we attach event handler functions to DOM elements, like a button, to react to certain events, right? And these event handler functions are also called callback functions, okay? So as the event happens, for example, a click, the callback function will be called. And here is how that actually works behind the scenes. So the first thing that actually happens after the event is that the callback function is put into the callback queue. Then, when the call stack is empty, the callback function is passed to the stack so that it can be executed. And this happens by something called the event loop. So basically, the event loop takes callback functions from the callback queue and puts them in the call stack so that they can be executed. And remember how I said in the last lecture that the event loop is how JavaScript's non-blocking concurrency model is implemented? Well, here is an overview of how that works. Now, we will go over why this makes JavaScript non-blocking in a special lecture about the event loop later in the course, because this is really a fundamental piece of JavaScript development that every developer needs to understand deeply. Alright, so as I already said, the focus in this course is on JavaScript in the browser, and that's why we analyzed the browser JavaScript runtime. However, it's also important to remember that JavaScript can exist outside of browsers, for example, in Node.js. And so here is what the Node.js JavaScript runtime looks like. It's pretty similar, but since we don't have a browser, of course we can't have the web APIs, because it's the browser who provides these. Instead, we have multiple C++ bindings and a so-called thread pool. Now, details don't matter here at all. I just want you to know that different JavaScript runtimes do exist. Alright, cool. That's all I had to tell you about JavaScript engines and runtimes. In this lecture, let's answer the question, how is JavaScript code executed? already know that it happens in a call stack in the engine, but let's dig a bit deeper now. And let's start by supposing that our code was just finished compiling, just in a way that we learned in the last lecture. So the code is now ready to be executed. What happens then is that a so-called global execution context is created for the top-level code. And top-level code is basically code that is not inside any function. So again, in the beginning, only the code that is outside of functions will be executed. And this makes sense, right? Functions should only be executed when they are called. And actually, we saw this happening already in our pick game project. So there we had an init function which initialized our entire project, but in order to actually initialize the game the first time that the page loaded, we needed to call that function immediately in our top-level code. And so that's what I mean here. But anyway, we can also see what top-level code is in this example here. So this name variable declaration is clearly top-level code, right? And therefore, it will be executed in the global execution context. Next, we have two functions, one expression and one declaration. So these will also be declared so that they can be called later. But the code inside the functions will only be executed when the functions are called. Okay, so we know that a global execution context is created for top-level code. But now, what exactly is an execution context? Well, an execution context is an abstract concept, but I define it basically as an environment in which a piece of JavaScript is executed. It's like a box that stores all the necessary information for some code to be executed, such as local variables or arguments passed into a function. So JavaScript code always runs inside an execution context. And to make this a bit more intuitive, let's imagine you order a pizza at a takeaway. So usually that pizza comes in a box, right? And it might also come with some other stuff that is necessary for you to eat the pizza, such as cutlery or a receipt, so that you can actually pay for the pizza before eating it. So in this analogy, the pizza is the JavaScript code to be executed, and the box is of course the execution context for our pizza. And that's because eating the pizza happens inside the box, which is then the environment for eating pizza. The box also contains cutlery, words, and to make the concept N1, and it's where top-level code will where the top level. And there is not a lot to say about the execution itself. It's just the computer CPU processing the machine code that it received. Okay, and once this first code, so the top-level code, is finished, functions finally start to execute as well. And here is how that works. For each and every function call, a new execution context will be created containing all the information that is necessary to run exactly that function. And the same goes for methods, of course, because they're simply functions attached to objects, remember? Anyway, all these execution contexts together make up the call stack that I mentioned before, but more on that in a second. Now, when all functions are done executing, the engine will basically keep waiting for callback functions to arrive so that it can execute these. For example, a callback function associated with a click event. And remember that it's the event loop who provides these new callback functions. Oh, now what an execution context is, but don't really know what it's made of. So what's the first thing that's inside? In this environment, all our variables and function declarations are stored, and there's also a special arguments object. This object contains, as the name says, all the arguments that were passed into the function that the current execution context belongs to. Because remember, each function gets its own execution context as soon as the function is called. So basically, all the variables that are somehow declared inside a function will end up in its variable environment. However, a function can also access variables outside of the function, and we have already seen that in action throughout this course, especially in the projects of the previous lectures. And this works because of something called the scope chain. And we will learn all about scoping and the scope chain later in this section. But for now, what you need to know is that the scope chain basically consists of references to variables that are located outside of the current function. And to keep track of the scope chain, it is stored in each execution context. Finally, each context also gets a special variable called the this keyword. And once more, there is a special lecture just about the this keyword later in the section. Okay, now the content of the execution context, so variable environment, scope chain, and this keyword, is generated in the so-called creation phase, which happens right before execution. And now just one final but very important detail that we need to keep in mind is that execution contexts belonging to arrow functions do not get their own arguments keyword, nor do they get the this keyword. Okay? So basically, arrow functions don't have the arguments object and the this keyword. Instead, they can use the arguments object and the this keyword from their closest regular function parent. And this is an extremely important detail to remember about arrow functions, and we will come back to it later. So these are the things that are necessary to run each function, as well as the code in the top level. Now behind the scenes, it's actually even more complex, but I think we're fine like this, aren't we? And now let's actually try to simulate the creation phase for this code example here. So, as you hopefully know by now, we will get one global execution context and one for each function. So one for the first function and one for the second function. In the global context, we have the name variable declaration, the first and second function declarations, as well as the x variable declaration. For the functions, the variable environment will literally contain all the code of a particular function. Now, the value of x is marked as unknown here because this value is the result of the first function that we didn't run yet, but we will simulate this in the next slide. Now, technically, none of these values actually become known during the creation phase, but only in the execution phase. So this is not 100% accurate here, but it's just to illustrate in mind. Anyway, now in the first function, we have the a variable set to 1 to become known. Finally, the variable environment of the second function contains the c variable set to 2, and since this is a regular function, so not an arrow function, is an array which contains, all this case, as you can see, that 7th engine. How will the engine keep track of the order in which functions were called? And how will it know where the stack finally comes in? And remember that the call stack, together with the memory heap, makes up the JavaScript engine. Well, it's basically a place where execution contexts get stacked on top of each other. So the execution context that it's finished running, it will be removed as. And using the analogy from before, it is a pizza box, and keep track which pizza belongs to each friend. Now all this sounds a bit abstract, doesn't it? And so to demonstrate how the call stack works, let's walk through this code example together so that I can show you exactly what happens. So once the code is compiled, top-level code will start execution. And then, as we learned in the beginning of the lecture, a global execution context will be created for the top-level code, right? So this is where all the code outside of any function will be executed. And what happens with this execution context? That's right, it our journey of diving really deep into how JavaScript actually works behind the scenes. I really hope you have enjoyed it so far and are able to see the immense value that these lectures bring to the table. Now, after this lecture, there will finally be another coding lecture, so hang tight, we're almost there. But now let's get started with this lecture. So we learned in the last lecture that each execution context has a variable environment, a scope chain, and a disk keyword. So in this lecture, let's learn what scope and the scope chain are, why they are so important, and how they work. And let's start by understanding what scoping actually means, and learn about some related concepts as well. So scoping controls how our program's variables are organized and accessed by the JavaScript engine. So basically, it written inside another function has access to the variables of the parent function. Okay? Air exact and in which a certain variable is declared. The variable environment, which is stored in the function's execution context. So if now you're asking yourself, what's the difference between scope and variable environment? Then the answer is that for the case of functions, it's basically the same. Now in JavaScript, we have the global scope, function scope, and block scope. And we will talk about these in a little bit. So the scope of a variable is basically the entire region of our code where a certain variable can be accessed. Now some people use the word scope for all of this, but I like to define all these concepts that we have here in a clear way because it should still types of scope in JavaScript for top-level code. Reference error. So JavaScript is trying to find the now variable, but starting in ES6, blocks also create scopes now. And with blocks, we mean everything that is between curly braces, such as the block of an if statement or a for loop. So just like with functions, variables declared inside restricted to the block. In ES6, all functions. And if you already know other programming languages, block scoping is probably more in line with what you already know. But I want to keep it simple here, and so I will only consider variable declarations and no functions, alright? Can access the H not work the other way around? A certain scope will never ever have access to the variables of an inner scope. Looking for variable C, but it's not there. And of course it isn't, because C is defined in the second function, and there is just no way in which the third function can access variables defined in the second function. And that is true even though it was the second function who called the third. And so here is even more proof that the order in which functions are called does not affect the scope chain at all. And so here, as a result, we get the reference error because both C and B cannot be found in the third scope nor in the scope chain. Okay, and with this, I hope I made it crystal clear that execution context, order of the execution context in the call stack. The scope chain does get the. But what's really important to note here is that the scope chain has nothing to do with the order in which functions were called. Or, in other words, the scope chain has nothing to do with the order of the execution context in the call stack. The scope chain does get the variable environments from the execution context, as shown by the red arrows here, but that's it. The order of function calls is not relevant to the scope chain at all. Alright? Really keep that in mind. Now, moving on to the second function now. Once again, its scope is equal to its variable environment. Also, it's lexically written within the first function, and so of course, it will have access to all its parent scopes as well. So we can say that the scope chain in a certain scope is equal to adding together all the variable environments of all the parent scopes. And so this is how scope and the scope chain are built in the JavaScript engine behind the scenes. Okay, now in the second function, we try to call the third function. But why does that work? Well, it works because the third function is in the scope chain of the second function scope, as we can see here in our scope chain diagram. It's a function in the global scope, or a global function, and therefore it's accessible everywhere. Of course, this will create a new scope along with the scope chain, as we already know. Great, so what happens in this third function? Well, we're trying to access variables B, C, D, and A here. B is no problem because it's right there in the third function scope, so that one is easy. Then variable C is not in a local scope, and so JavaScript needs to do a variable lookup. So it looks up in the scope chain, looking for variable C, but it's not there. And of course it isn't, because C is defined in the second function, and there is just no way in which the third function can access variables defined in the second function. And that is true even though it was the second function who called the third. And so here is even more proof that the order in which functions are called does not affect the scope chain at all. And so here, as a result, we get the reference error because both C and B cannot be found in the third scope nor in the scope chain. Okay, and with this, I hope I made it crystal clear. The next topic we need to talk about is a very misunderstood concept in JavaScript, and that is hoisting. So we learned that an execution context always contains three parts: a variable environment, the scope chain in the current context, and the disk keyword. We already learned about the scope chain, and so now it's time to take a closer look at the variable environment, and in particular, at how variables are actually created in JavaScript. So in JavaScript, we have a mechanism called hoisting, and hoisting basically makes some types of variables accessible, or let's say usable, in the code before they are actually declared in the code. Now, many people simply define hoisting by saying that variables are magically lifted or moved to the top of their scope, for example, to the top of a function. And that is actually what hoisting looks like on the surface. But behind the scenes, that's in fact not what happens. Instead, behind the scenes, the code is basically scanned for variable declarations before it is executed. So this happens during the so-called creation phase of the execution context that we talked about before. Then, for each variable that is found in the code, a new property is created in a variable environment object. And that's how hoisting really works. Now, hoisting does not work the same for all variable types. And so let's analyze the way hoisting works for function declarations, variables defined with var, variables defined with let or const, and function expressions, and also arrow functions. So function declarations because they are stored in a variable environment object even before the code starts executing. And I actually told you before that function declarations work this way, but now you understand why. It is because of hoisting. And just to make this table a bit more complete, so that it serves as a nice overview for you, I also show here that function declarations are block scoped, as we learned before. Just keep in mind that this is only true for strict mode. So if you're using sloppy mode, which you shouldn't, then functions are function scoped. Next, variables declared with var are also hoisted, but hoisting works in a different way here. So unlike functions, when we try to access a var variable before it's declared in the code, we don't get the declared value, but we get undefined. And this is a really weird behavior for beginners. You might expect that you simply get an error when using a variable before declaring it, or to get the actual value, but not to get undefined. Because getting undefined is and actually, this behavior is a common source of bugs in JavaScript. So this is one of the main reasons why in modern JavaScript, we almost never use var. Now, on the other hand, they are actually hoisted, but their value is basically set to uninitialized. So there is no value to work with at all. And so in practice, it is as if hoisting was not happening at all. Instead, we say that these variables are placed in a so-called temporal dead zone, or TDZ, which makes it so that we can't access the variables between the beginning of the scope and the place where the variables are declared. So as a consequence, if we attempt to use a let or const variable before it's declared, we get an error. Also, keep in mind that let and const are block scoped, so they exist only in the block in which they were created. And all these factors together is basically the reason why let and const were first introduced into the language, and why we use them now instead of var in modern JavaScript. Okay, but now, what about function expressions and arrow functions? How does hoisting work for these? Well, it depends if they were created using var or const or let. Because keep in mind that these functions are simply variables, and so they behave the exact same way as variables in regard to hoisting. This means that a function expression or arrow function created with var is hoisted to undefined, but if created with let or const, it's not usable before it's declared in the code, because of the temporal dead zone. So again, just like normal variables, right? And this is actually the reason why I told you earlier that we cannot use function expressions before we write them in the code, unlike function declarations. Okay, but now before finishing, let's take a more detailed look at this mysterious temporal dead zone. So in this example code, we're going to look at the job variable. It is a const, so it's scoped only to this if block, and it's going to be accessible starting from the line where it's defined. Why? Well, because there is this temporal dead zone for the job variable. It's basically the region of the scope in which the variable is defined, but can't be used in any way. So it is as if the variable didn't even exist. Now, if we still tried to access the variable while in the TDZ, like we actually do in the first line of this if block, then we get a reference error telling us that we can't access job before initialization. So exactly as we learned in the last slide, right? However, if we tried to access a variable that was actually never even created, like in the last line here, where we want to log x, then we get a different error message saying that x is not defined at all. What this means is that job is, in fact, in the temporal dead zone, where it is still initialized, but the engine knows that it will eventually be initialized, because it already read the code before and set the job variable in the variable environment to uninitialized. Then, when execution reaches the line where the variable is declared, it is removed from the temporal dead zone, and it's then safe to use. So, to recap, basically each and every let and const variable get their own temporal dead zone that starts at the beginning of the scope until the line where it is defined. And the variable is only safe to use after the TDZ, so the temporal dead zone. Alright, now what is actually the need for JavaScript to have a temporal dead zone? Well, the main reason that the TDZ was introduced in ES6 is that the behavior I described before makes it way easier to avoid and catch errors. Because using a variable that is set to undefined before it's actually declared can cause serious bugs which might be hard to find. And I'll show you a small example in the next lecture. So accessing variables before declaration is bad practice and should be avoided. And the best way to avoid it is by simply getting an error when we attempt to do so. And smaller reason why the TDZ exists too. So as you know, we can't reassign const variables. So it would not be possible to set const should never be reached the declaration. And that makes it impossible to use the variable before. Okay? Make sense? Positive execution actually reaches the declaration. And that makes it impossible to use the variable before. Okay? Make sense? Now, if hoisting creates so many problems, why does it exist in the first place? I get this question all the time, and so let's quickly talk about it here. So the creator of JavaScript basically implemented hoisting so that we can use function declarations before we use them. Because this is essential for some programming techniques, such as mutual recursion. Some people also think that it makes code a lot more readable. Now the fact that it also works for var declarations is because that was the only way hoisting could be implemented at the time. So the hoisting of var variables is basically just a byproduct of hoisting functions. And it probably seemed like a good idea to simply set variables to undefined, which in hindsight is not really that great. But we need to remember that JavaScript was never intended to become the huge programming language that it is today. Also, we can't remove this feature from the language now, and so we just use let and const to work around this. Maybe it didn't seem like it, but hoisting is actually a fairly straightforward process. So let's just go through the different scenarios here, starting with variables. So let's just create 3 variables here, so that's to you. Here, in fact, what will happen now, result, is that we are and then here we are trying to call undefined works, but now let's show me a very cool example to declare variables, and let if you really need to change the variable later. Also, in order to write clean code, you should declare your variables at the top of each scope. That will just make your code at least look a little bit better. After the declaration are hoisted. So just don't practice this in the bar here. Let's just take 2 minutes to see yet another small difference between them. So let's again declare one variable for each, and the window object has been, of course, z here. And so let's now take a look here at the window object here in the console. And is the global object of JavaScript in the browser. And you can see all kinds of stuff in here. For example, the alert window that we have used before, or also some other functions that we probably might have used already before. So I'm not going to go into that here. But what is important, let's go all the way to down here, and you can of course explore this by yourself in case you're interested in. But what matters here is that beside all these functions, we also get a property of x equals 1. And that's exactly the variable that we declared right here using the var keyword. However, we cannot find y or z here anywhere in this object. And that's because they were declared with let or const. And so variables declared that way do not create properties on the window object. So let me actually demonstrate this to you even better. So we can say, or we can test x equal window dot x. So here we are testing if x is actually a property of the window object. And so if it is, then of course x must be the same as window dot x. And actually it is true. And now the same for y and z. And so in these cases, it is both false. So in conclusion, I just wanted to let you know that variables declared with var will create a property on the global window object. And that can have some implications in some cases. And again, you can take some time to explore the window object because it's quite interesting to see everything that is in there. All right, but with that being said, let's now finally move on to our next topic, which is going to be the this keyword. The this keyword is an extremely important concept to understand in in JavaScript, and many beginners find it especially difficult. But don't worry, it's actually not that hard if you know exactly how this keyword works. So the this keyword, or this variable, is basically a special variable that is created for every execution context, and therefore any function. In fact, we learned before that it's one of the three components of any execution context, along with the variable environment and scope chain that we already learned about before. Now, in general terms, the this keyword will always take the value of the owner of the function in which the this keyword is used. We also say that it points to the owner of that function. And that sounds very abstract, but we will see what that means in a second. For now, what's very important to understand is that the value of the this keyword is not static, so it's not always the same. It depends on how the function is actually called, and its value is only assigned when the function is actually called. So it's very different from a normal value in this regard. If we set, for example, x to 5, then x will always just be 5. But the this keyword, again, depends on the way in which a function is called. But what does that actually mean? Well, let's analyze 4 different ways in which functions can be called. And the first way to call a function is as a method, so as a function attached to an object. So when we call a method, the this keyword inside that method will simply point to the object on which the method is called. Or, in other words, it points to the object that is calling the method. Okay? And so let's illustrate this with a simple example. So the method here is the callH method, again, because it's a function attached to the Jonas object. In the last line here, we then call the method, and as you see, inside the method, we use the this keyword. Now, according to what we just learned, what should be the value of the this keyword here? And that's right, it should be Jonas, because that is the object that is calling the method down there in the last line, isn't it? And so then on Jonas, we can of course access all the properties that it has. And so this .year will become 1989 because that's Jonas.year as well. So in this case, writing Jonas.year would have the exact same effect as this .year. But doing it this way is a way better solution for many reasons that we will get into throughout the course. And we will play around with this example a bit more in the next video. But anyway, another way we call functions is by simply calling them as normal functions. So not as a method, and so not attached to any object. In this case, the this keyword will simply be undefined. However, that is only valid for strict mode. So if you're not in strict mode, this will actually point to the global object, which in case of the browser is the window object. And that can be very problematic, and so this is yet another very good reason to always use strict mode. Next, we have arrow functions. And while arrow functions are not exactly a way of calling functions, it's an important kind of function that we need to consider. Because remember, arrow functions do not get their own this keyword. Instead, if you use the this variable in an arrow function, it will simply be the this keyword of the surrounding function, so of the parent function. And in technical terms, this is called the lexical this keyword, because it simply gets picked up from the outer lexical scope of the arrow function. So never ever forget this very important property of arrow functions. Believe me that actually I run into 1 or 2 bugs because of this behavior. Okay, so it's really important not to forget that arrow functions do not get their own this keyword. Okay, and finally, if a function is called as an event listener, then the this keyword will always point to the DOM element that the handler function is attached to. Very straightforward, right? Now, the this keyword is usually a big source of confusion for beginners, but if you know these rules, then it should become a lot simpler. And to make it even simpler, it's also important to know what the this keyword is not. So this will never point to the function in which we are using it. Also, the this keyword will never point to the variable environment of the function. And these are 2 pretty common misconceptions, and so that's why I'm addressing them here. Okay? So again, the rules that I showed you here is all that you need to know. Alright, and now just for the sake of completion, there are actually other ways in which we can call a function. For example, using the new keyword or the call, apply, and bind methods. But we don't know yet what any of these are, and so we'll talk about how this keyword works with them when the time comes. Anyway, that's it for this lecture, so let's now use this in practice to make it crystal clear. Let's now see the rules of how the this keyword is defined in action. And let's start by taking a look at the this keyword outside of any function whatsoever. So just outside here in the global scope. And so we get that the this keyword in the global scope is simply the window object. So that's the global. To finish this section, we're going to do one more deep dive into yet another fundamental aspect of how JavaScript works. Get. From this, we can already to the console, we now get a mutated object here. Let's now create a similar example to the one that we had in the last video so that we can explore this idea of object references that we just learned about in the previous lecture, but now by writing some code. So let's start, which remember is this array right here, and then let's place a few more names in here, because basically when Jessica marries, she gets some, and so here, she wanted to. Welcome back to part 2. There's actually nothing to learn yet. The execution context of the call notice how I said engine, which is that these objects are no longer needed, and that the memory occupied by them. Welcome back to part 2 of memory management, and this one is all about how memory is released. In particular, we're going to dive deep into how a mechanism called garbage collection works behind the scenes in order to keep our memory clean and healthy. So remember how in JavaScript, each value that we create goes through a memory lifecycle where first, memory is allocated for the value, then the allocated piece of memory is used, and finally, when no longer needed, the piece of memory is released. Now we already talked in depth about step 1. Step 2 is pretty obvious, so there's actually nothing to learn there. And so let's now turn our attention to the way in which memory is released in the JavaScript engine in step 3. So basically, we're going to answer the question, how is memory freed up after we no longer need a certain value? Now, since these values are stored in the stack and the heap, we need to analyze both these storage mechanisms. So first off, in the call stack, it's all very simple, because the variable environments where primitives are stored are simply deleted when the corresponding execution context pops off the stack. So as an example, here is the call stack with the global execution context of the call function has variables y and z. So these 3 variables are clearly stored in the call stack. And so then, as the execution context pops off the stack, the variable environment of the call function will just be removed from memory together with the execution context that just popped off the stack. So as I said, very simple, right? Variables are simply stored in an execution context in the call stack, and as soon as the context is gone, so are the variables. And the memory that they occupy is simply released for future usage. Now, notice what happens with the x variable in the global execution context. Since this execution context never disappears, this value will stay in the stack forever. Now, this is no big deal. I just wanted to make it clear that global variables will, of course, never be deleted, which is pretty intuitive, I think. Okay, but now let's move on to the heap, where memory management is considerably more complex. So, in order to delete old, unused objects from the heap and free up memory, JavaScript engines employ a process called garbage collection. This garbage collection is the central tool for memory management in any JavaScript engine. And notice how I said engine here, because it's indeed the engine that runs garbage collection automatically whenever it sees fit. We developers cannot control when the heap memory is cleared by garbage collection, which is actually a great thing, because this automatic memory management makes our lives a lot easier. So you can basically think of garbage collection as an automatic cleaning service that comes into your house from time to time and identifies and removes old stuff that no one is using anymore. But anyway, there are different ways to implement garbage collection, but all modern engines use an algorithm called mark and sweep. And let's now quickly check out how it works by bringing back the call stack and heap. Now, first of all, here in red and green, we have objects called hobbies and tasks, and so, as we just learned previously, these variables actually store references to the actual object stored in the heap. Let's now also say that the red object references some other object, which of course is also stored in the heap, and the green object references just another object. And by the way, I keep saying objects that are stored in the heap, but as we just learned earlier, these can actually be not just objects, but also arrays, functions, and other data structures like sets or maps. Okay, but now back to the mark and sweep algorithm. So the first step of garbage collection with the mark and sweep algorithm is the mark phase, where all objects that are reachable from a so-called root are marked as alive. Now, roots are basically starting points from which the algorithm starts to look for alive or reachable objects. And different things can be roots, but the most obvious ones are the global execution context, which is always present, and any other execution context of running functions. So again, the algorithm starts looking for objects in these places called roots. So in this example, the green and red objects are obviously alive, because they can be reached from one of the roots. And the same is true for the blue and gray objects. They are also alive because they can also be reached from one of the other reachable objects. But now let's take it one step further, because an object can be reached by more than just the global execution context or one of the other contexts in the stack. They can also be reached by event listeners or active timers, or by something that we call closures. And more about closures later. So these two are also roots for the mark and sweep algorithm. And now let's say that we have this purple object that is referenced and therefore reachable from an active timer, and this yellow object that is reachable from a closure. So both these are alive as well. And now finally, just to make this a bit more complete, let's imagine that we also have this pink object in the heap, which isn't being referenced by anything. And so this one is not marked as alive because it cannot be reached by any of the roots. So we can basically say that this one is dead. Okay, so with this, we basically just simulated the mark phase. So phase 1 in the mark and sweep algorithm. The second phase is the sweep phase, where all the unmarked objects, or in other words, all the unreachable objects, are simply deleted. Basically, the algorithm has decided in the first step that these objects are no longer needed, and that the memory occupied by them can be reclaimed and used for future memory allocations for future objects. So to simulate this in our example here, right now we only have one object that is unreachable, and that's the pink object. So what's going to happen in this phase? Well, that's right. And so just like this, the automatic garbage collection has ensured that our memory stays nice and clean, and not cluttered with objects underneath in the heap. Alright, but now what happens when the getTask function finishes execution and its context pops off the stack? Well, let's simulate that our garbage collection runs again. And again, I want to just emphasize that there is no way to control or trigger garbage collection manually from our code. We also have no way of knowing when and how often garbage collection happens. It depends on a few factors, like how much memory our app is consuming, how much memory is available, which JavaScript engine the browser is using, and so on. But anyway, for the sake of this example, let's say the garbage collection algorithm runs again at this point. So now, with the getTasks variable environment gone, there's really no one to reference the green object anymore, right? Therefore, the green object and also the blue object are no longer reachable from any root. They're no longer alive. Therefore, as the process moves into the sweep phase, both the green and the blue objects will be swept away, and the memory that they occupied will be reclaimed. Okay, but now let's turn our attention to the red object, and let's ask ourselves the question, how could this object ever be deleted? Well, the answer is that it can't. The red object will never be deleted, so it will stay in the heap forever, because the global execution context will never disappear. So this root will always exist, and will always be able to reach the red object collected, even if we no longer need it in our code. And what about the purple and yellow objects? What if our app also no longer needs those objects? Well, this idea of an object being no longer needed actually brings us to our final topic of this lecture, which is memory leaks. So a memory leak happens when an object that is actually no longer needed by our application is incorrectly still reachable by the garbage collector from one of the roots. As a result, the object is marked as alive and is not deleted. Again, even though we actually no longer need it in our code. So it should be deleted, but it can't. And you can think of a memory leak basically like forgetting to throw away some stuff that you no longer need. And so this will then clutter up your house unnecessarily. But back to JavaScript, this happens when an object is still incorrectly referenced from somewhere. And one major source of these wrong and undesired references are alt and unnecessary event listeners and timers. If, for example, a timer creates an object, this object will always be reachable, unless the developer actively deletes the timer when they no longer need it. Otherwise, if the timer just stays around and keeps running, it will forever reference the unnecessary object, causing a memory leak. The same is true for an event listener that might no longer be needed at some point. So, in order to avoid memory leaks, make sure to always deactivate timers and event listeners when they're no longer required, especially if they reference large objects. Also avoid declaring large objects as global objects, because these will also never be garbage collected, as we just saw earlier. So that's going to lead to memory leaks as well. Now, memory leaks can be a huge topic. Object is marked as alive and is not deleted. Again, even though we actually no longer need it in our code. So it should be deleted, but it can't. And you can think of a memory leak basically like forgetting to throw away some stuff that you no longer need. And so this will then clutter up your house unnecessarily. But back to JavaScript, this happens when an object is still incorrectly referenced from somewhere. And one major source of these wrong and undesired references are alt and unnecessary event listeners and timers. If, for example, a timer creates an object, this object will always be reachable, unless the developer actively deletes the timer when they no longer need it. Otherwise, if the timer just stays around and keeps running, it will forever reference the unnecessary object, causing a memory leak. The same is true for an event listener that might no longer be needed at some point. So, in order to avoid memory leaks, make sure to always deactivate timers and event listeners when they're no longer required, especially if they reference large objects. Also avoid declaring large objects as global objects, because these will also never be garbage collected, as we just saw earlier. So that's going to lead to memory leaks as well. Now, memory leaks can be a huge topic, but there's no need to dig even deeper into it at this point. Alright, so this is a brief overview of how the garbage collection process works. It's going to run over and over inside the user's browser while they're using the application, making sure that memory stays clean and uncluttered of objects that are no longer necessary over time. Now, in reality, memory management is way more complex than just this. It's an extremely complicated process. There are actually multiple heaps. Objects are moved from one heap to another depending on their age. The garbage collector has multiple algorithms for the different heaps, like generational garbage collection, and so on. But I'm absolutely sure that this broad overview that you just learned about is more than enough at this point. So this already gives you a great idea of how memory is automatically managed inside the engine. And now, before we move on, I need to quickly mention 4 more big topics about how JavaScript works behind the scenes that are not in this section, but closer to where we actually need to learn about them. The first one, which I actually just mentioned in the last slide, is closures. So we're going to dive really deep into closures once we reach the closer look at functions section. Next, one of the most fundamental concepts of JavaScript is prototypal inheritance, but we're only going to talk about that in the object-oriented programming section of this course, because it doesn't make sense to learn about this now, only to forget it all until we finally reach that section. The same is true for a detailed lecture on the event loop. We already introduced the event loop in this deep into how exact JavaScript entered the scenes as well in the advanced DOM, and with this, behind the scenes. It would be of them were hard and confusing concept 100% of everything reaching the end of this who have no idea about sticking with it to the end. Take a break, and I see you in the next section.
Don't write any asynchronous code. Make them simple synchronous code लिख देता हूँ एक बारी को. Let me write very simple synchronous code. Function sum a comma b. To the last section for the day, which is the architecture for asynchronous JavaScript code. इससे थोड़ा ज़्यादा clear होगा कि why exactly it behaves this way. Why is it that I keep on dancing even when 3 washing machines are waiting for my attention? The answer is how the JavaScript runtime was written, or specifically the async runtime was written. Whoever wrote this decided कि उनको ऐसे लिखना था. They could have decided to write over here. See the code that you see over here. How does it move across the JavaScript stack? The asynchronous JavaScript stack. So asynchronous JavaScript stack. Notice the things on the right. There is a call stack section. ये हर language में mostly होता है. Most languages have stacks. There are 2 types of languages. Stack-based languages and register-based languages. Most languages we deal with are stack-based languages. So they have this concept of a call stack. If you've done a compiler design, you might have seen this. इसका काम ये होता है कि as functions are getting called, they keep on getting pushed to this call stack. So if I don't write any asynchronous code, make them simple synchronous code लिख देता हूँ एक बारी को. Let me write very simple synchronous code. Function sum a comma b, return a plus b. Function sub a comma b, return a minus b. Function, that's it, I guess. Simple thing. I call sum 1 comma 2. I call sub 1 comma 2. And let's say, let a x equal to this thing, let y equal to this thing, console.log x, console.log y. When I write this only synchronous code, there is no fs.read file here, there is no set timeout here, there is no set interval here. तो ये तीनों किसी काम के नहीं है. The web APIs section, the callback queue, and the event loop. Web APIs section, callback queue, event loop are useless and not used at all for normal synchronous code. तो जब मैं इसको रन करूंगा, what will happen? ये दो फंक्शन रजिस्टर होंगे. The sum function will get pushed to the call stack. कि अब इसको रन करना है. This function will actually run. It will get popped from the call stack. Then the sum function will get pushed to the call stack. It will run. It will get popped from the call stack. The console.log function will get pushed. Minus v run होता है. Console.log is pushed, popped, pushed, popped. So if I do this, it will get pushed to the call stack. It will run. It will get popped from the call stack. The console.log function will get pushed to the call stack. It will actually execute and print the thing, pop to the call stack, so on. So if I do this, notice some function gets pushed. A plus b run होता है. Sub function gets pushed. A plus b minus b run होता है. Console.log is pushed, pop, pushed, pop. I've only called functions one at a time. इसमें but gets pushed. A plus b run होता है. Sub function gets pushed. A plus b minus b run होता है. Console.log is pushed, pop, pushed, pop. Right, so on. So if I do this, notice some function gets pushed. A plus b run होता है. Sub function gets pushed. A plus b minus b run होता है. Console.log is pushed, pop, pushed, pop. I've only called functions one at a time, but let me make one function call another function, so it becomes a little more. We can see the call stack actually filling up as functions or calling functions. So if I write something like this, like we did before, function, or let's just do some random calls here. Let's say sum for some random reason calls sum with ANL. It does nothing with the return value. ऐसे ही कॉल करता है. जब सम कॉल हो रहा है तो randomly sum को कॉल कर दे रहा है. Sum is returning some value, but we are not storing it anywhere. Just vaguest function call. तो when I run this, अब जब sub यहाँ पे push होगा, sub के अंदर sum function call होगी, तो sum उसके बाद push होगा. As a function calls another function, you will see them getting active. क्या उसने a plus b हुआ वापस आया, उसने a minus b किया वापस आया, and then if I run this, sum call हुआ, a plus b call हुआ, pop call. Sum call हुआ, उसने sum को call किया, उसने call stack. As that function executes completely, you will see it get popped from the call stack. If I run this, sum call हुआ, a plus b call हुआ, pop call. Sum call हुआ, उसने sum को call किया, उसने a plus b हुआ वापस आया, उसने a minus b किया वापस आया, and then console.log. It clocks synchronously. This is all that you would need. You would not need to answer a complicated question of what are callback queues in an interview. अगर language में simple होती, but unfortunately language is complicated. It is complicated for good reasons. Making it asynchronous, frees up your CPU to do other things while your asynchronous tasks are running separately. So this is where let's look at a separate code. Let's say I write this set timeout, a function called callback. Sol.log callback call. Let's call callback after 1 second. Let's also call callback after 2 seconds. Let's also call callback after 3 seconds. And इसके नीचे let me write a for. Assume this is a very long for loop. अभी ऐसा है कि ये कोड ना धीरे-धीरे execute होता है. This code executes slowly line by line so that we can visualize it. But assume this is a very long for loop. What did we saw while back? If this is a very long for loop, doesn't matter how many callbacks are waiting to be executed. They don't get executed until the thread becomes free, until X gets printed and the thread becomes free. Then it starts to print the first callback, second callback, third callback. Let's see it in action. What actually happens when you click on run is the first set timeout starts to run separately here. एक clock अलग से चालू हो गई है. It is not on the main JavaScript call stack or thread. Its job is simply to see कि क्या 1 second हो गया. Has 1 second passed, and as soon as 1 second passed, it can't push. क्या इसको रन करने लग जाओ. It can't push directly to the call stack. That's not how the architecture was written for this JavaScript runtime. Web APIs section, the separate section, it's called Web APIs because basically set timeouts is not part of the standard JavaScript spec or fs.read file. JavaScript का part नहीं है, language का part नहीं है. It's something that is needed for websites, for browsers, not fs.read file but set timeout, which is why this is called the Web API section. Okay, ये सारी APIs जो हैं usually web के अंदर होती हैं. Fetch, XML, HTTP, read, whatever that function is, the predecessor of fetch or set timeout, are functions that are not necessarily part of JavaScript but browser JavaScript, which is why this is called the Web API section. Whenever you call set timeout, यहाँ पे let's say clock चल रही है, and when the clock ends, it can't interrupt the current call stack. It can't say कि इसको चलाना बंद कर दो, मेरे को चलाओ. It can't say stop running what you're doing, run this. All it can do is push to a callback queue and hope that eventually the call stack here becomes empty. Eventually all the synchronous code finishes, and then when it finishes, the event loop pulls the next thing from here to here, pushes it here, and then that function starts to execute. When that is done, pulls the next thing, so on and so forth. That is why when I run this, first clock is being maintained, done. Second clock is being maintained, खत्म. Third clock is being maintained, खत्म. But the callbacks are waiting in the queue. अभी तो ये for loop ही चल रही है. This for loop will run 10 times. Once it is done, as I said, it's running slowly, which is why ideally तो ये बहुत जल्दी रन हो जाएगा. But if this was very big for loop, it will keep on running and on the call stack. And the 3 set timeouts are waiting in the callback queue to be run. They are not directly moved from here to here. They are moved from here to here. And when this condition is met, then the first callback is pulled. First callback is called. खाली हो गया. Second thing is pulled. Second is called. खाली हो गया. Third thing is pulled. Third is called. That is why they wait and what might feel like अच्छा 1 second हो गया तो ये function call होगा. You might feel कि after 1 second this function might get called. It doesn't happen because the JavaScript runtime is written in a way all asynchronous operations have to wait in a queue and don't directly get to interrupt the call stack. So similarly, if I had a set interval like we had written a while back, every 1 second call this callback. The set interval will Okay, this doesn't visualize set intervals. Otherwise, it would have been nice for us to see a bunch of callbacks here. But ये website only works for set time and not set intervals, which is why we don't see anything here. But there's a lot of questions that come out of this. Mostly questions around what will run first, will this run first, will this run first, and what happens when I do this set interval callback 0, not set 0. But still, since it reaches the web API section, it checks that 0 second run time. It is only able to push it back to the callback queue, and hence X will get printed first. Even though I'm only waiting for 0 seconds, which is almost equivalent to me just calling callback. But since I didn't set timeout, it will reach the web API section for a second, and then will get pushed to the callback queue. And only when the thread becomes free will get pulled over here. Even if it says 0 over here, still पहले X print होगा, बाद में callback will get printed. There are a lot of assignments that can be given on this. We'll try to give those to you guys soon enough. How many of us understand why asynchronous operations work the way they do? What are the benefits of doing this? And the general architecture of async. Now, one thing that's left is promises. जो दिमाग actually खराब करेंगे. But do we understand callbacks? Do we understand callback-based asynchronous function calls? Which is what we've learned today. What we have not learned is promise-based asynchronous function calls that are going to break your backs and make you leave computer science forever. That we'll do in the next class. 88% understood. Open to questions after this. I think we can officially end the class. Yeah, I think one thing you guys want to see, we're slowly reaching the end of Super30, and placements have been great. So keep at it and keep doing what you're doing. Let me show you the placements until this point. I was very anxious in this Super30 because we did not have the best filtering criteria. The interviews weren't as good, but people have been doing really well. I suddenly remembered एक दो लोगों ने मुझे मना किया था अपना नाम लिखाने से. So I'll try to not scroll बहुत ज़्यादा नीचे because they're on the trials. They didn't want to share. So let me zoom in a bit so that नीचे वाले नाम जो हैं थोड़े छुप जाएं. हाँ, तो you see a few names are a little older of the names, but this number has reached 40, and average median is really high. Even the lower ones, जिनकी मतलब 9 lakh का start हुई थी, उनकी बढ़ती जा रही है धीरे-धीरे. 9 से 11 होगी 2 महीने में, so on and so forth. So everyone's doing well. The list is long, but I will stop here. किसके नीचे इनके नाम हैं? They've told me not to share yet because the trial is still on. But basically all closer, greater than 10 LP for sure. Average much higher. I think average is $2,000 a month. Median is $1,500 a month. Which is great starting. Mostly entry level. Like almost no one had any experience. Almost everyone is in college or very recently graduated. Very less people have some experience. So it is sort of possible. Just not the only thing you need is a lot of proof of work and in-depth fundamental knowledge, a lot of interest, and maybe some network to get into that company or whatever referral. Which is very possible. And, I become very overly bearish when I see it will come out and then things just stay normal and I talk to founders and became same only कि भाई फिर वही developer ही चाहिए काम करने के. Probably stay that way, but I don't think I will change. This is not today. Not tomorrow. What was AJ comes and some tool comes like it changes. But again, it just hasn't changed at all. Every month the numbers sort of remains the same. $2,000 a month. Median is $1,500, $1,600 a month. Which is a great starting. Mostly entry level. Like almost no one had any experience. Almost everyone is in college or very recently graduated. Very less people have some experience. So it is sort of possible in this market. The only thing you need is a lot of proof of work and in-depth fundamental knowledge. A lot of interest and maybe some network to get into that company or whatever, a referral. But very possible. And I become very overly bearish when I see a tool come out and then things just stay normal and I talk to founders and it becomes very same only कि भाई फिर वही developer ही चाहिए काम करने के लिए. Probably stay that way. But I don't think I would change honestly. This is my opinion today. Now tomorrow, God knows, AGI comes and some tool comes, it changes. But again, it just hasn't changed at all. I mean, every month the numbers sort of remains the same. We're able to maintain a decent frequency. In Super30, we're aiming for 50. We'll probably cross that very easily by the time Super30 ends. It's fairly possible, I think. If you guys keep at it, मेहनत करते रहोगे तो होता रहेगा. With that, I will end the class officially for everyone. And for the people who have questions, I'm open to answering them. I'm looking at Q&A for the next 10-15 minutes. Have an HTTP server. पर ही चाहिए काम करने के लिए. Probably stay that way. But I don't think I would change honestly. This is my opinion today. Now tomorrow, God knows, AGI comes and some tool comes, it changes. But again, it just hasn't changed at all. I mean, every month the numbers sort of remains the same. We're able to maintain a decent frequency. In Super30, we're aiming for 50. We'll probably cross that very easily by the time Super30 ends. It's fairly possible, I think. If you guys keep at it, मेहनत करते रहोगे तो होता रहेगा. With that, I will end the class officially for everyone. And for the people who have questions, I'm open to answering them. I'm looking at Q&A for the next 10-15 minutes. and get comfortable with the syntax, you will see a bunch of assignments come. You said some thread checks the time given in set time on JS is single threaded. But notice ये जो web API section है ये अलग है. So the JavaScript thread is not the thread that is doing this. There is another thread in the CPU in the browser or in Node.js that is actually maintaining these things. So now you might suggest that JavaScript is multi-threaded, but no. Over here JavaScript is single-threaded. When they say it's single-threaded, they compare it to multi-threaded languages like Java or Rust, where you can actually spawn a bunch of threads and synchronize data between them. Versus JavaScript doesn't let you do that. But yes, if you really look at it, you can say it's dually threaded. कि दूसरा thread यहाँ पे कुछ तो कर रहा है. Yes, there is a different thread that is separately doing something. But the actual code execution is being done by a single thread. Versus in Rust and Java, the code execution can actually be parallelized amongst multiple threads. So there is a nuance to the statement of it is a single thread. Assignment for advanced people can come. There was a Super30 assignment. That is not released yet, but it will release on Tuesday. So on Tuesday we can send it to you as well. Mikey remind or just ask Rahul and share it here. Let's say you're running some JavaScript code in a server. A request comes while the request is executing, another request comes. Is JavaScript single threaded? How will the server handle it? What a beautiful question, yaar. Hitesh bhai. क्या प्यारा सवाल पूछा है. The question is, the question states कि if I have an HTTP server that is receiving a bunch of requests, one after the other, but JavaScript is single threaded, does that mean मैं एक time में एक request handle कर सकता हूँ? That's exactly what we learned today. Happens on what is happening inside the request. Now, if inside the request you are running a for loop from 1 to a million, then yes, एक time पे एक ही handle होगी. The first one will come, control will come. It will run a very long for loop from 1 to a million. After it is done, it will respond, and then it will move to the second request. It will run a for loop from 1 to a million. After it is done, return the second request, then the third request will start. But if you're not doing a CPU intensive task, which is generally what happens in backends, कि जब एक request आती है, what you are actually running is not a CPU intensive task, but an IO intensive task, which is talking to a database and retrieving data from there, talking to Redis or a queue, putting data there, retrieving data from there. That is why you can handle multiple requests together, because most operations that are happening when a request comes are not CPU intensive for loops, but IO intensive DB calls and Redis calls and maybe file system calls, generally DB calls, which are IO heavy. But yes, if they are CPU heavy, or even if you send a million requests on Node.js server, yes, it might break, because irrespective of how big the machine is, if it has 8 CPUs or 16, all the CPU tasks are run on a single CPU and a single thread. And there are ways to make it better and run it on all threads, but that's not technically multi-threading, it's something else. We'll learn that when we reach, cluster module and how to make Node.js more optimal. Let's say that another request comes to server. What happens? How will the server maintain context state of these requests? Okay, CPU intensive task doesn't matter. IO intensive tasks, every task might start together. The JavaScript thread might send a DB call in the first request and then move on to the second request after all three of these requests are met. Even request coming is sort of an asynchronous function call. We see this on each request. In the end, there's a callback function that gets called whenever a request comes. So basically all of these requests. So yes, you have to scale yourself. There's nothing much you can do in a single server. If we have a Foco machine, should we run 4 Node.js processes to run properly? That is correct. That is yes, 100% true. If you have 8 core machines, I run 8 different processes for Node.js. For Rust or Go, you should write multi-threaded code that runs 8 different, not threads, but there are various terms for these things in various languages. For example, in case of Go, you should run thousands of Go routines or millions of Go routines. In case of Rust, you should run a bunch of async tasks or Tokyo tasks, or generally run 16 threads on 16 core machine. A single process can run multiple threads. A single process in Go can run multiple Go routines. A single process in Rust can run multiple tasks that can run various threads. But a single process cannot use all of your cores in Node.js. You have to start multiple processes. At the OS level, you have 8 processes running in case of Node, but at the OS level, you only have 1 process running that is starting multiple threads or multiple tasks in case of Rust. That's the difference between the two. When the new Super30 start, it most probably starts 1st of April. Yeah, 15th of April, something like data from there, talking to Redis or a queue, putting data there, retrieving data from there. That is why you can handle multiple requests together. Because most operations that are happening when the request comes are not CPU intensive for loops, but IO intensive DB calls and Redis calls and maybe file system calls, generally DB calls, which are IO heavy. But yes, if they are CPU heavy, or even if you send a million requests on Node.js server, yes, it might break, because irrespective of how big the machine is, if it has 8 CPUs or 16, all the CPU tasks are running on a single CPU and a single thread. And there are ways to make it better and run it on all threads, but that's not technically multi-threading, it's something else. We'll learn that when we reach, cluster module and how to make Node.js more optimal. Let's say that in the request coming to server, what happens? How will the server maintain context state of these requests? Okay, CPU intensive task doesn't matter. I would intensive tasks. Every task might start together. Right? The JavaScript thread might send a DB call in the first request and then move on to the second request. After all, three of these requests are not. Even a request coming is sort of an asynchronous function call. We'll see this when we reach express. In the end, there is a callback function that gets called whenever a new request comes. So, basically all of these requests. Then yes, you have to scale your server. There's nothing much, you can do in a single server. If we have a 4-core machine, should we run 4 Node.js processes to run properly? That is correct. That is a yes, 100% true. If you have an 8-core machine, you should ideally run 8 different processes. For Node.js, for Rust or Go, you should write multi-threaded code that runs, 8 different, not threads, but there are various terms for these things in various languages. For example, in case of Go, you should run thousands of Go routines or millions of Go routines. In case of Rust, you should run a bunch of async tasks or Tokyo tasks, or generally run 16 threads on a 16-core machine. A single process can run multiple threads. A single process in Go can run multiple Go routines. A single process in Rust can run multiple tasks that can run on various threads. But a single process cannot use all of your cores in Node.js. You have to start multiple processes. At the OS level, you have 8 processes running in case of Node, but at the OS level, you only have 1 process running that is starting multiple threads or multiple tasks in case of Rust. That's the difference between the two. When a new Super30 start, it most probably will start 1st of April. Yeah, 15th of April, something like that. Do we have to remember JavaScript predefined functions, async functions? When a new Super30 start, 1 process running that is starting multiple threads or multiple tasks. You have to start multiple processes. At the OS level, you have 8 processes running in case of Node, but at the OS level, you only have 1 process running that is starting multiple threads or multiple tasks in case of Rust. That's the difference between the two. When a new Super30 start, it most probably will start 1st of April. Yeah, 15th of April, something like that. Do we have to remember JavaScript predefined functions, async functions? Yes, you do. That is exactly what will be asked in interviews if you're planning for Super30. All right, more questions. What is the reuse of read file sync? Then when read file is so much better. I mean, sometimes I actually have a good answer to this that I'm not remembering now. Okay, in some cases it might make sense, but what is that case? There is actually no case where it might make sense to read files synchronously. Honestly, just cleaner code, I guess. अगर आपको 3 files को एक के बाद एक ही read करना है, if you have to read 3 files one after the other, then this is just a little more cleaner to look at. Const fs equal to 8, and whatever you can 8. पूरी file one read करो, then पूरी file read करो, then पूरी file read करो, one after the other. Let's say the requirement is like this. Then you can write a more optimal code like this, or you can write a less optimal code that you see above. Because you can automatically tell the one above is much more easier to read compared to the one below. This thing that you see over here is called callback help. That will understand when we reach promises. But ease of reading, this is so much easier to read and write compared to what is happening over here. That might be probably the only reason you might want to use sync versus async. Some resources to learn about SMTP. I don't think there's any way do you want to create one yourself? There is this self-hosting SMTP service called Tap. Because again, deploying one is easy, but then there are reputation metrics on if Google thinks your SMTP server is well. I mean, if you just have to use an SMTP server, it's much easier. But creating one is difficult because all the shit or whatever, if I can like another year or two. Are callbacks async await? Then same? No, they're very different. Callbacks and promises are very different. We'll understand promises, you'll understand the difference between the two. Which code word is better, Telegram or Ledger Nano? Telegram and game. I use a Ledger. You can choose whatever you want, but I just take that. If 3 is about something called however you pronounce it, but I have never used this. This is OG sort of been working for many years. I just take that. Does internship encompass you to get a job 10 LP as a fresher or not enough? Generally enough. If you're in college, it's just easier to crack an internship, convert full time compared to not. I will have to convert only, or it does convert and then does not. What is that for the command? See, it's like very hard to read, bro. Scale 26H144. God, it's been like a while since I've written these and seen these. Yeah, it's like very hard for me to read, honestly. From what I can tell, you have creating an M3 U8. From the looks of it, looks fine. There's probably a much simpler command to create, whatever, convert to a 56 ratio and whatever, create an M3 U8. This is a slightly more complicated one. Every time I've done it, and I've seen, these systems being deployed in production for videos that are being uploaded, thousands of videos a day, and it just works. There's no simple reason for why this might not work. Although, okay, I see it now. You have an RTMP input. This is where things get tricky. Actually, no, I'm sorry, I'm wrong. Easier than debugging, it might just make sense to use the Nginx RTMP output into an M3 that you start a bunch of flags, it exposes an RTMP URL for you, so rather converts it to a Web3 assignment. Notice it shows me Phantom, Sulfur, Backpack, and Salt, and I go to tensor dot, stored as an extension. That's not the point of making an extension. The point is that any website should be able to, if I have a wallet installed and I go to tensor.trade and I click on connect wallet, your wallet should appear automatically over there. For example, if I go here and click on connect wallet, notice it. It should not in the Web3 class. Have a good night, folks. Bye bye.
backend is huge, and if we start discussing every single component that could be part of it, we will be stuck here for years. So what we will do is, we will only discuss those topics which are used in majority of the code bases, let's say 90% of them. With that in mind, let's talk about HTTP protocol, the medium through which our browsers talk to our servers, either to send data or to receive data from it. And as I said, there are a lot of other ways and protocols which clients and servers use to communicate with each other. And HTTP being one of the most used ones, we will focus on that. Now, there are two ideas which are at the heart of HTTP protocol. The first one being statelessness. What does it mean? Statelessness basically means it has no memory of past interactions. So each HTTP request carries all the necessary information for the server to process it, such as headers or URLs and methods, which you will see in a bit. And after the server responds, it forgets about the request. If the client makes another request, the server treats it as a new and unrelated event. And it also means self-contained requests. Since the server does not remember past requests, each request must include all the necessary data, such as authentication tokens or